I was silly with a whole bunch of microphones hanging on. So silly. I wonder if this will actually make this pick up better, the audio of the louder. It probably won't matter.
Huh?
So I'm on the speaker now, a noticeable difference.
It will definitely change things. Let's see. Can you say something?
All right. How's this sound?
Well, right now there's nothing there.
It's not on. Okay, now I try now. No, it was supposed to be on down here.
Well, we need to actually set up the microphone.
Oh, okay, that's also a problem.
Then we'll know. And the headphone go. So, actually, where did the other headphones go?
Oh, they're right there.
Okay. Oh, so you want to use your own?
Yeah, if you don't mind.
Yeah, sure.
Is this a good line? Can you see this one here?
Just a moment. We shall drop it in.
Go with that stand.
You just okay. Actually, okay. Yeah. Keep on talking. Talk. Left.
Left.
Stop.
Stop. Okay.
Yeah. Okay. Now talk normally.
All right. I'll probably talk about this volume when I'm actually speaking.
Perfect.
All right.
Okay. Now I think you're clipping a little bit. I think we need to tune it down one notch. Okay.
All right. Is it better?
Yeah.
This is probably actually kind of loud. No, I'll probably talk like this.
Okay. Can you stand in the middle again?
Yes.
No, I mean just we just need to focus on you.
I look really silly with all these microphones hanging on.
You should have worn a checkered shirt.
I'm sorry. I didn't wear it. You're wearing a checkered shirt this
well,
time.
actually-
No, it's not you. Okay. They are very good.
Okay, I should be lighting up in cyan right now.
Yeah, they're a little small for this, but I can still get it pretty well.
Okay,
Nice, that'll do.
good. So for anybody who's curious, this is manual focus and using focus peaking. So basically run the digital picture on the image and with a lot of pictures other things that means also the channel or contact and separate. And we want to prevent the autofocus from going off while the recording is on. It's the opposite of machine learning.
Oh, I have this much space, really? Maybe that doesn't quite work all the way over there.
No, it actually works up to there.
Okay.
So I can definitely see the edge.
Okay.
So
I wonder if we can also on the. Yeah, we can on the cast too. Okay. Cool.
The only issue is if you stand to the left of the line, we won't see you. But we'll still see you.
What was that?
If you stand to the left of the line, we won't see you, but we'll still see you.
Yeah. Well, that's. I could be out of the frame for 2 seconds. I can play.
Okay.
All right, let's get started. All right, hello everyone. Welcome back to the morning session. I assume people will kind of filter in as we go. Yeah, there it is, only 9 a.m. In this lecture, I'm going to talk about actually a variety of topics that kind of build on the lecture from last time, or my lecture from last time. But we also are going to be fairly fast and fairly high level. In particular, I'm going to cover, we talked yesterday, and you saw in later lectures too, about a bunch of different machine learning algorithms. In particular, I talked about support vector machines, linear regression, and logistic regression. Still pretty helpful for them, but at least I gave the loss function and kind of wrote it down a little bit more explicitly, the formulation for these algorithms. And today what I want to do is just highlight a few other algorithms that you may run into as well as you study machine learning, and it's kind of are exposed to machine learning algorithms. And this is going to be even higher level. Some of them will be covered in great depth by further lectures in the course. Some of them will not be. But they are quite common, and so you should sort of know what these are. And the goal of this was really just to highlight the fact that a lot of different algorithms can be cast in this same framework of hypothesis class, loss function, and optimization algorithm. I'll then talk very briefly about another kind of learning, which is called unsupervised learning. Today, I believe, we'll also hear a lecture on reinforcement learning, which is yet another type of machine learning approach. But unsupervised learning is quite common. And so we'll talk about a few ways of interpreting that in a few different algorithms. Finally, I'll get to probability. So far, I've really been light on probability. I haven't really mentioned it at all. You've seen a little bit maybe in subsequent lectures. But I want to at least highlight how probability can enter into this framework of hypothesis class, loss function, and optimization algorithm. Because there actually are very close and tight-knit connections between these two, and it's good to at least understand from a high level how probability can enter into the equation here. Though of course, probabilistic models are a much bigger topic, and there are entire courses on these things, so this is going to be a very light treatment. And finally, I'll have 2 slides on evaluating machine learning algorithms. Mainly taking some, similar to what Alex said, there are certain things that people do wrong when it comes to evaluating methods, and I want to just highlight a couple of these. Though I think actually I would say that what I'm going to talk about here is I see this less and less these days, the mistake people can make. All right, so let's start with a couple other machine learning algorithms. Remember, the framework we had yesterday was that there were kind of 3 ingredients to a machine learning algorithm, right? There was, first of all, a hypothesis class. We call this H beta. Secondly, there was the loss function. And this was different based upon whether we were talking about a regression problem or a classification problem, but there were also different possible loss functions for regression and different possible loss functions for classification, which lead to different algorithms in machine learning. And then finally, there was an optimization method. And the main ones I talked about yesterday were, for most problems, gradient descent type algorithms, and you'll see a lot more of that going forward, gradient type methods, and stochastic gradient methods. I also talked about exact solutions for least squares, at least. I'll talk more about optimization in general on Friday's lectures. But for now, I just want to highlight the fact that these algorithms, these different machine learning algorithms, can be looked at in this framework, as long as you consider the fact that they can also use different optimization algorithms. All right, so let's just jump right in. Here are a bunch of classes of machine learning algorithms, some of which you've heard, some of which you might not have heard of, which, though they aren't always presented this way, fall very nicely into this framework. So the first one is a very broad class called kernel methods. Now you'll hear a lot more about kernel methods next week. Andrew Wilson is going to be giving 2 lectures on these. And while this is a very, very simplified treatment here, and there's much more depth to these, in some sense, kernel methods can be thought of like a linear predictor. They're actually very similar. In particular, for a kernel method, the hypothesis class is the following. It's a linear function, much like a linear regression case, or any linear hypothesis class. Sum from I equals 1 to m of theta I times this function k of x and xi. Okay, a couple things here to note. First of all, and actually this function k is called a kernel function, and it essentially, intuitively, it evaluates some kind of similarity between how similar x is to xi, how similar these 2 arguments are, where bigger means more similar. And a couple things to note here. First of all, this hypothesis class is still linear in the parameters theta, so you can still use almost all the same loss functions and or optimization methods. These actually are very used for how you actually optimize these things. And you can use all the same different sort of loss functions and optimization methods as we were doing with, say, a linear classifier or a linear regression. All right, that leads to different class of algorithms for these different loss functions. Now, a couple points to take home. First of all, I'm wrapping a lot of complexity around this k function here, and really this is a very, very inexact and high-level treatment of kernels. You'll see much more. There are a lot of ways to interpret exactly what this kernel function is doing, including embedding the data into a higher dimension with very high-dimensional input vectors, though without ever actually constructing these things explicitly. That's one interpretation of this. Another interpretation is sort of a even more theoretical one about inner product spaces and these kind of things, but I'm not sure if even Andrew will get that in detail. But the other thing to notice is 2 things here. First of all, unlike before, where we had, sort of our input vector was, remember, a vector that has n dimensions, and we have m different examples. The thing to notice here is that I'm actually taking the sum from I equals 1 to m. And so I have to compute this kernel function between my input, my new input and my hypothesis on, and all the examples in my training set. Remember, the sum over I here is indexing not over just the parameters, but also over all the examples in the training set. And this means 2 things. This means, first of all, there was a discussion yesterday about sort of the relative size of the parameters and the number of examples we had. And here they're actually the same. So here we have the same number of parameters, theta, as examples. We actually have m of them, so m equals n in this case. And that means these issues that we at least touched on, like overfitting and how you deal with that, you can't just sweep them under the rug. You have to deal with those things. And it's typically dealt with by regularization. So if you add regularization to your loss function here and minimize that, minimize the sum of loss functions over this leads to what we typically think of as kernel methods. The second point this also relates to is the fact that to compute my hypothesis or my prediction on a new example, I have to compute some function of that example and all my training data. So that means I have to keep all my training, at least without optimizations, I should say. I have to keep all my training data around. Right? I sort of store it in memory. And every time I want to make a new prediction, I have to do a complete pass over all my data. Now, as you might imagine, for big problems, that becomes very inefficient. And so a lot of work, and sort of the exciting work, really, and what makes kernels scalable to large problems, is the fact that there are ways to approximate this. And oftentimes, they're actually exploiting the sort of more, the other interpretation of what this kernel function is. So by exploiting that properly, you can come up with ways of approximating this very closely that actually don't require you to keep all your data around. But at least the naive kernel method does require you to keep all your data around. So that's kernel methods. One slide. Again, we'll see a lot more of this. Another class of methods, which I'll just touch on briefly, because you may also see this, is called nearest neighbor methods. Nearest neighbor methods are interesting. What they do is very simple. What you do to make a prediction is you look for the most similar example in your data set, and you just predict the same label as what you saw there. For both regression or classification, you can do either one. So this notation here, I'm saying that H, this is kernel, this is nearest neighbor. I'm saying that H theta of X equals Y. And this is kind of a little annotation here, but remember Y with index over, Y sub whatever says the, Y sub I says the ith for any example in our data. And so here what we do is we pick whichever example Y is closest to our input. And the way we write that here is we say the argmin over J. So what that says is whichever parameter J minimizes this thing to come, pick that J. And we're going to say, well, I just realized I haven't, I guess it's the argument over I. Argument over I. X minus xi. Okay, and I think we saw this yesterday, actually, this notation here, but just in case you haven't seen it before, this term here is the 2 norms squared of a vector, which is just equal to all the elements squared. Okay, so essentially if you take a difference here, take a 2 norms squared, that is actually kind of a measure of how far away those two vectors are. So what we do is we just, Right, so what we do is we just look for, given the input to our fluxus function h, we look for the thing in our training data that is closest to that in this distance, and we pick that one and predict that output. You can also do the closest k of them. This is called k nearest neighbor, and you can take the average of the k closest ones, but it's essentially a very similar type method. Now, one thing to note here is that this method here requires no real training, right? We don't actually have to fit, there already kind of are no parameters here. I mean, theta doesn't really enter in here. And just like the kernel functions, this also means, though, that we have to keep all the data around in order to make our prediction, right? Because we have to search for every time we want to make a prediction, we have to search through all the data to find the closest one and predict that, the corresponding output. I forget if I said this or not, but essentially these are called non-parametric methods. Kernels are also called non-parametric. It's important to note that non-parametric does not mean there are no parameters. What it really means is that the number of parameters is growing with the size of the data. So we do not have a fixed number of parameters, rather we have a variable number of parameters that depend on the size of our data set. And these are sort of nearest neighbor methods are one of kind of the classic non-parametric examples, because here there actually essentially are no parameters. I mean, maybe you have some parameters on how you want to do that distance function, but we won't worry about it. Okay, neural networks you've seen already. There's going to be much more today, so I won't go on this. Neural networks essentially are nonlinear classifiers where you have some nonlinear function, like nonlinear activation function, like the sigmoid function we talked about before. And you get the final output by composing many of these nonlinear functions together. So the hypothesis class is this nonlinear function here. Loss function is the can usually be squared error between your output and your input. And optimization is things like grade descent or stochastic gradient descent. Now, one important thing is that unlike a lot of other methods so far we've talked about, there's no guarantee that you're going to find the actual optimal set of parameters for a neural network. But this is actually typically okay. You can typically still find pretty good ones using the methods that Kwok's going to talk about later today. And there have been some real sort of major successes for these in recent years. They're sort of a very exciting topic these days again. They were before, now they're coming back. Or actually have come back for a while, I suppose. All right, a couple more. I think there's two more. One more type of classifier machine learning algorithms here called decision trees. These are actually one of the first machine learning algorithms, or sort of at least one of the first ones to really gain traction as machine learning algorithms and called machine learning. And what these do is these partition the input space into different regions by essentially looking at a single variable and branching on that variable. So for example, if we have a two-dimensional input and we want to say predict a binary classification task, then what this tree here says is we first look to see if the second coordinate is greater than or less than 2. If it is, yes, we go down this path. If it's not, we go down this path. So if it is greater than 2, we just predict -1. If it's not, we look to see if the first coordinate is greater than -3 or not. If it is, then we put, so if it is, then we predict -1. If it's not, we predict +1. So essentially, they just go through kind of this list of rules in a tree form and make the final prediction. So our hypothesis class here actually ends up being kind of a tree structure that will partition the data set into different regions. Now, at each final node here, you can either just make a single prediction, just say this is just going to be, if I ever get here, I'm just always going to predict +1. But you can also extend this to actually have linear regression functions at the roots. At the leaves of the tree, or even more complicated functions. And I think actually one of the functions that Nano talked about yesterday was kind of like that. You would partition the space, and then at each root, at each leaf, you would have a Gaussian process that determine your function. So these can be very, very powerful here. So our hypothesis class in this case is these partitionings of the space. The loss function for typical decision trees is a little bit more complex, but you actually can look at standard ways of training decision trees as minimizing kind of something that's sort of like logistic loss. It actually ends up being not quite that, but it is sort of a probabilistic type loss, which I'll get to later. That's the loss function they're optimizing. But the real key here is that unlike a lot of the classes we've seen before, I guess other than neural networks, there's no real way to optimize exactly over the class of all decision trees, right? We can't, like with linear regression, just find the optimal solution, find the optimal tree. So what we do instead is we actually kind of really split the data in a way that starts making the most progress towards minimizing that loss function. So essentially, we have some loss function. It's kind of like a probabilistic loss. And we pick the first node in order to most minimize that loss. And that we can do. We pick one node to minimize loss. Then we branch upon that one node. And then for those two subsequent nodes, we do this process again. So this, you can think of this kind of as a greedy type of optimization that tries at each iteration to minimize this loss function over one coordinate at a time. Again, sort of very high level here, but that's kind of what decision trees are doing. And you will see these a lot. Now, you actually don't see them much on their own anymore. What you typically see them is combined with what's called an ensemble method. What these are, very generally speaking, is ensemble methods. I won't write out the class for the decision tree because it's actually a lot easier to see it graphically. An ensemble method is really just a combination of other hypotheses. So our final hypothesis is just going to equal some weighted combination, say over k other hypothesis classes. Now our parameters here are just say the weights on those different classes. And of course, each sub-hypothesis here would have its own set of parameters. So we should really write this as theta being both the parameters for the weighting and the parameters on each individual hypothesis class. But I'm just sort of using brief notation here. Some that you might have heard of in particular are two very common types, and these actually both often use decision trees as the individual hypotheses here. So they're kind of stacking these things in a very nice way. One is random forests, and that is essentially an ensemble of decision trees, because many trees are a forest, where each tree is built on different subsets of the data. It's a very simple idea, but actually it ends up, if you just sort of want a simple algorithm that will perform well on a lot of problems, random forests do very, very well. They're sort of a very robust algorithm. You do well on a lot of different problems. Another one you might have heard about is boosting. Boosting is also a way of combining different classifiers, again, often decision trees. And you can actually view boosting as minimizing, so the hypothesis class is an ensemble method where each hypothesis is, say, a tree. The loss function ends up being an exponential loss function. So this is one I didn't really talk about too much, but it was on the slides before. Exponential loss is one of them. And boosting actually, it looks like again, kind of a greedy optimization approach to minimizing exponential loss with whatever hypothesis class you want as the base classifier. So that's sort of a very brief overview. I didn't really do any sort of justice to all these methods. But the thing to sort of keep in mind is you probably will see these algorithms as you work in machine learning. And it's good to at least know that though the fit isn't always perfect, they weren't really developed necessarily with this kind of framework in mind. You can still typically actually view them this way. So it's very easy to think of these algorithms as having a hypothesis class, minimizing some loss function, using some optimization method. And you can fit most algorithms into that framework, at least most supervised algorithms. Okay, so again, very brief, but you'll see a lot more detail about some of these. All right, so let's talk about now, again, very shortly, about unsupervised learning. So remember that our basic pipeline for supervised learning, we have some training data, so we have some state digits and their corresponding labels. We use machine learning to come up with some hypothesis function such that when we apply it to training data, it kind of gives us approximately the outputs that we want. And then we make predictions based upon new data that we don't have the labels for. Right, that's the overall pipeline. Now, unsupervised learning seems really hard because basically we have the same pipeline, except we take away the labels. We don't tell it anything about what these outputs should be. And it seems like kind of everything we've talked about so far will kind of break down then, right? Because now, I mean, the whole point of this hypothesis class, right? Not right here. The whole point was that we had, some input xi. We had some input xi, right? And we wanted it to be the case that when we applied our hypothesis function to this, this was approximately equal to the corresponding yi. This is how we measure loss then, the difference between these two things. How can we do this when we don't have yi's anymore? Right? So our setting is somewhat the same. We have still our input features. We still have some model parameters. And I think now I'm just going to abandon, I sort of done it slowly, but lecture before, the number of parameters was always equal to the size of the input vectors. But actually, if you look at almost all the things I've shown you before, the other hypothesis classes, this is not the case anymore. So I'm just going to abandon that for now and just call my model parameters, say that there's some other size, k. We have k different parameters, which is not always the same as our input size. A little less time, but I'm going to now refer to theta as being rk. So we have this same setup. We have some model parameters. We have some input features. But what does this even mean, right? What's the point? What do we do here when we don't have any outputs to aim our hypotheses towards? And there's actually a couple of ways to view unsupervised learning. But one interpretation that actually encompasses a lot of different unsupervised learning methods is to say that unsupervised learning is really about trying, in some sense, to reconstruct the input data. Okay? So we're trying to take, so we have a hypothesis function as before. We're going to do something kind of strange. We're going to say that we don't have y's, so I actually want my hypothesis function when I apply it to xi to be approximately equal to xi. Okay? So this now means our hypothesis class is no longer a function mapping from xn to, rn to r. Our hypothesis function is now going to be a mapping from Rn to Rn. And we want it to be chosen, or we want to choose our parameters rather, such that xi, we find a hypothesis function that approximately equals xi. That sounds weird to you. Hold on a sec, because it seems like we could do this really easily, right? And you wouldn't really learn very much. And similarly, the loss function now, because we're measuring the distance between these two things, we need a loss function that's also going to accept two input vectors as inputs. So the loss function will now be a mapping from Rn by Rn to R plus two dimension n vectors as input, and we get an output. And a common one, for example, would just be that distance we saw before when we were measuring like the nearest neighbor, when we were finding nearest neighbors of functions. And this is just sort of the generalization of squared loss to multivariate inputs. And so a common one, for example, would just be to say that the thing we're trying to minimize here, that's just going to be the 2 norm of the difference between these two things. Square 2 norm. That doesn't really matter if it's square or not. Oops. Okay, does that make sense? Any questions about sort of the setup here?
Is there a minus sign on the right hand side?
A minus sign. Oh. Yes. That's a good question. All right. So, of course, the obvious question that maybe you're all thinking about is that this seems kind of silly, right? Because we could just choose H to output whatever we input into it, and that would give us 0 loss. And it wouldn't really, we wouldn't, there would be essentially no parameters, and we wouldn't really have learned anything. Clearly wouldn't have learned anything, right? Because there's just no, why not just choose H theta of x equals x? What's preventing us? Well, of course, to stop this, what we have to do is restrict the class of functions we can consider in our hypothesis class, right? We can't consider sort of all possible functions, or even let alone all functions. We can't even consider any function class that would include this function, because that would clearly minimize the loss, and it wouldn't give us any information. So what we have to do instead is somehow restrict this hypothesis class to not allow that, and to force the function, in some sense, to need to extract some structure out of the data in order to actually come up with a hypothesis function that can minimize this loss. And in fact, just like our problem for supervised learning, we kind of have one canonical minimization problem that kind of fit a lot of these things. We can do the same for classification. So, or sorry, for unsupervised learning. So we can write a lot of these problems as minimize What, I'm just writing a lot of tables in work here today. Minimize for theta, sum from I equals 1 to m of L H theta xi. So this becomes kind of our, just like we had the canonical loss minimization for classification and regression, this is the one for unsupervised learning. So I think the best way to see this actually is rather than just sort of thinking this conceptually, is let's look at two examples. Look at two examples that both fit into this framework, though they seem quite different. These two algorithms are called k-means and principal component analysis. And they're typically taught not in this kind of framework, but you can do them both in this framework. Okay, so I'm just going to cover them very briefly, to kind of get the intuition, but focus upon how they actually do fit in this framework. Let's get a new board. We'll do this. Well, you're going to have to, unfortunately, I think. You can see the very top of the screen, right? So say that hypothesis function or that minimization function. Okay. All right, so let's look at k-means. What k-means says is that our parameters are going to be a set of k different points in the input space. I'm going to call those mu1 to mu k. For each of these is the same size as the input vector. Okay? And our hypothesis class, we can't just sort of pick any output we want. We have to output one of those k numbers as our prediction that we're going to, compare to our input value x. All right, so our hypothesis class, we have to output one of these k numbers. And of course, if you want to sort of do any reasonable job of this, you'll probably pick the one closest, in fact, to your input. So the hypothesis function ends up being mu, and again, this is kind of cumbersome notation here, but you pick the mu such that it minimizes the distance between x and mu. Right, so you look at, compare all of these to the different mu, compare the x to all the different mu's, and just pick the one, return the one that minimizes this distance. And then given that, I just want to minimize the sort of standard optimization problem here. Now, unlike a lot of the things we've seen before, though I guess similar to algorithms like neural networks, we can't solve this exactly. It ends up being this kind of hypothesis class here. You can't really, it isn't so nice to take gradients from this. It's just, you can't really, unlike least squares, you can't write down an exact solution of this. There's a typical way to actually solve this, rather than the things we've seen, exactly the things we've seen before, is to actually alternate between two steps. So what you do in the first step is you find, for all the data points in your training set, you find the closest mean to those. Right, so you find whichever mean is, in fact, the minimizer here. And then you just recompute that mean to be all the things that are assigned to it. Essentially, all the examples in your data set that were closest to that mean, you take the new mean to be the mean of those examples. Okay? So, kind of very high level there, but hopefully the intuition comes across that we are trying to minimize squared loss here. This is our hypothesis class. And the intuition, the way we're limiting ourselves, is that we're restricting our hypothesis to only output one of these k values. Therefore, we can't just always output the input, right? Because there's just not, as long as you have m greater than k, you can't just output the input always. You have to figure out what are the k's, or sort of what are the means that most closely, that sort of do the best job of minimizing that loss. Any questions?
Is this center necessarily x, or can it be not? Can it not be one of the x's?
These mu's?
Yeah,
They don't have to be the x's. They can be anything. They're just numbers. They're just vectors in Rn. No, they definitely don't have to be the x's. In the optimization procedure, sort of a way of actually minimizing this loss is to set them to be averages of different xi's, but that's kind of incidental. I'm actually kind of glossing that intentionally because the high level point here is that you're just trying to pick those means that minimize this loss. And the way this is sort of typically seen, you might see a picture of this, which I didn't really want to highlight too much, but if you have some data that looks like this, well, and you have, say, two different means, well, a good strategy would be to pick one mean to be here, because this one would be the output for all the guys in here, and one mean kind of here, because that would be the output, one's closest to all the x's in here. And so what you do essentially is, hopefully if you do a good job of optimizing, you'll assign at some point these to one cluster and these to another cluster, and then you'll find the means appropriately, and then everything works well. Yeah?
How do you choose a good value of k?
Good value of k, it's a great question. So, much like all the other problems we've had here, for example, the same thing with how do you choose a good value of lambda if you're regularizing? How do you do these things? A good way of doing this is actually through cross-validation, too. So what you can do is you can compute this loss. You can, again, divide the training set into inputs and outputs. Sorry, divide the training set into training and validation without any outputs here. And use the validation set to evaluate this loss. Right? Now, this doesn't work quite as well for clustering as it does for classification or regression, but you can still use the same point actually. And one of the advantages of this loss formulation is that it actually kind of makes clear what you're trying to solve. And so this sort of separation can actually work. It can give you something. Whereas a lot of sort of typical views of k-means, it's just kind of, well, that looks like two things here, I'll pick two. That works great for 2 dimensions, sometimes there aren't even clear two clusters here. But what's really nice about this loss function formulation is you can do the same thing, and you can use a holdout validation set to actually evaluate how many clusters you should pick. So another algorithm that fits into this exact same framework, well, the general framework up there, is principal component analysis. And here, so this here, this here is k-means. And this here is component analysis. And the idea here is that the outputs that we're going to predict, they're no longer from some fixed class of inputs. Instead, they're going to lie on a lower dimensional space. And the way we write that formally is the following. Say that our hypothesis, first of all, our parameters are going to be two matrices. Theta 1, theta 2. The sizes are here, I won't bother writing those. Theta 1 is going to be n by k. Theta 2 is going to be k by n. So these are matrices now. And we have k less than n. So for example, theta 2 is going to be a fat matrix. Theta 1 will be a skinny matrix. And the hypothesis class says, I'm going to output the following. Theta 1 times theta 2 times x. Okay, and we didn't really cover linear algebra here, so if this is a little bit confusing, don't worry about it. Essentially what this is doing is, because theta 2 is of lower dimension than x, this operation here forces this vector to take on, to be a vector in Rk. And And since k is less than n, this vector here has less information in it than the original input vector. Then we multiply by this thing here, which will put us back into the original space of our n, so we can compare with our examples. But essentially what's happening here is that this step here is kind of compressing the data. We have to throw away information. We can't keep it all anymore. One way of looking at this visually is to think of this like the following. And I should also say that okay, so with this function here, we again just solve that problem. That leads to this optimization problem. This one is also non-convex. Don't look at that other two there. It's the same as all the other norms we have. This problem is also not what we typically think of as a solvable problem, but it actually ends up being a case that this is one of the few problems that we actually can solve efficiently, even though it's not what's called a convex problem. So we actually can solve this using something called an eigenvalue decomposition. All right, so we can find the exact solution here, even though it might not look like we can at first. Yeah?
So the hypothesis class that you've written is theta 1 into x, right? So you can basically keep k greater than n and get you can still calculate the loss.
You can keep k greater than n. So k is greater than n. It's a little bit odd, right? Because then you have this function back in your class, right? The function of h of theta equals x is still in your class. You just take these to be identity matrices. So let's say k equals n here. These are both the identity. That means just your hypothesis is predict what you saw as input. So you can do that, but it isn't very useful. You don't get a lot of value out of it. The actual value of PCA comes from the fact that you are compressing the data. And so you are finding this reduced dimension the data lies in, and then projecting it back into the higher dimension. One way of doing this, if this is your data originally, so say you have two-dimensional input data, and theta, and say k, so n here is 2, and pick k to be equal to 1. Okay? What this looks like graphically is you have to take all your data and essentially find the line that you want to predict it all lies on. So you want to predict the points, this one here, this one here, this one here, this one here. So the closest points to these data points that lie on a line. And what PCA is actually doing is it's finding, so essentially when you do this operation, you get a one-dimensional quantity that says where you lie along this line, and then you project back into 2 dimensions. That gives you sort of this figure again, but they'll all lie on this one line here. And what's happening here is that essentially PCA is picking both of these points, what they actually are, and the best line you could draw through your data. Now, of course, in higher dimensions, n can be 10, and if k was 2, then you'd be finding the best plane that fits through those dimensions. Higher, you're finding a good hyperplane that fits through that. Yeah?
So we've written it, doesn't your line need to go through the origin for this example? Because h of 0 was 0.
Okay, that's a good point, yeah. So the way I'm also doing this is I'm also talking, so, okay, good point. If x is the original dimension, you can always do the same trick where you add 1 to it. There's two things you can do here. The first is you can add 1 to your input vector and kind of get away from this. The better thing to do actually is to, before you apply PCA, to actually center your data around the origin, so that actually you just subtract the mean off, so that actually this, I didn't write any axes here, so I'm actually fine to do this. So I almost lied to you. This I didn't know. This was 0, 0 here, of course. That's what I meant. So you can do that too. You can do either one. This is probably the better one. There's another question over there. Okay. All right. So that's all I'm going to say about unsupervised learning. It's a very big field, but and not always presented this way. But I think you can view it in a very similar framework. There's a lot of value in viewing it in the same kind of philosophy. All right. Second to last thing, probability. So I've somehow managed, as I mentioned yesterday, to avoid talking about probability when talking about machine learning for almost 3 hours. But of course, these things are very tied together. And the reason, really, probabilistic models underlie a huge range of machine learning algorithms. And, I use things like logistic loss and kind of said there's some probabilistic interpretation here. And same with least squares. There's actually a reason, or there can be a reason, why we choose the square loss function as opposed to anything else. And really, probabilistic models underlie a lot of the basic choices of machine learning. And they also let us interpret the results in a better way that actually captures sort of how we are uncertain about the data. And that's really where probabilistic models can come in handy, because they can give you not just a prediction, they can let you interpret that in terms of maybe how certain you are about your predictions. So let's think about this for a second. Why did we pick the squared loss? When we did a linear regression, I said, let's use this loss function that minimizes, takes the distance between the output that we predicted and the true output, and we predict, our loss rather is the square difference there. Why did we choose that? And one answer that I gave yesterday was, well, we choose it because it's easy to optimize and it's kind of nice. And that's actually a perfectly good reason. But we can think of other reasons too. And actually, one of the motivations for why we use squared loss comes from probability. So here's the idea. This is a very general concept. It's used all over the place in machine learning, and it would probably be a bad idea to not mention it at all in a lecture on machine learning. The idea is the following. We're going to hypothesize that the outputs on our data set are not just almost equal to the hypothesis, they're actually equal to the hypothesis class. There actually is, say, some underlying model that outputs the y's as the hypothesis class. That could be, either a linear function there, some other hypothesis class, etc. But we don't actually observe the real outputs here. What we observe is the output plus some noise term. So in particular, all our yi's we observe are the true hypothesis class plus some noise term. And one very common noise term would be a Gaussian random variable. So this is the density of a Gaussian random variable here. That's probability density of that form. Another way to write this would be to say, well, just rearrange terms here. One thing we can write is we can write the probability of y, really the probability density of y, given x and parameterized by theta. That's sort of this whole thing here. The probability of this is also given by a Gaussian density. So this also equals 1 over 32 pi sigma x negative h theta x minus y squared over 2 sigma squared. Sigma here is the variance of this Gaussian distribution, but actually ends up not, if you assume it's some known quantity, it actually ends up not affecting what kind of loss function we get. And now you do the following. Now what we're going to do is we're going to say, okay, I'm defining a model this way. I'm defining what's the probability of my output, of an output given an input and parameterized by some theta. What I want to do, what we originally to do here, if I want to choose theta based upon this model, this probabilistic model, is to choose the theta that maximizes what I actually saw. Okay, so what I saw was a bunch of y's and x's. If we assume furthermore these are all independent and identically distributed random variables, so they all have this same distribution here, and they're all independent from each other, then we can write the probability of what we saw, namely y1 through ym, as a product of all those probabilities evaluated at the data points that we've seen. And a reasonable thing to do then would be to pick the thetas that make that probability as high as possible. So that makes sense? So basically, what we have is we have the probability of our data. So given a bunch of xi's and yi's, the probability of our data is going to be equal to the product of all these terms, probability of yi given xi, parameterized by theta. And we want to just find the theta that maximizes this. Okay, so this is kind of a probabilistic approach here, because what we're doing is we're defining a probabilistic model for our data based upon some parameters. And by the way, these parameters, the way those come in is they determine the hypothesis function, much in the same way of our old setting. But this is really a probabilistic model that we have here. And we're going to pick the thetas that maximize the probability of what we observed. Does that make sense? Okay. Now, a few very simple steps here shows that when this problem here is equivalent to minimizing over theta of just the square errors. Essentially what happens is you maximizing the product here is the same as, or maximizing the product here is the same as maximizing the log of this thing. Log is a monotonic function, so you could either maximize this or maximize the log. The nice thing about logs is it lets you turn this product into a sum. So you can go from maximizing a product of things to maximizing a log of things, and while we're at it, let's just take it one step further and minimize. Let's talk about minimizing somewhere else. Minimize a negative log, some of the log terms here. Now we're going to plug in our exponential function here. We take logs, you get a log of this term, the log cancels out the exponent there, and so what you get is you get this log term here plus 1 over 2 sigma squared times this squared loss term here, and that's just equivalent to this, right? This term here does not depend on theta at all, so we don't need to ignore it. This term here, though it has a sigma in it, it doesn't really matter because it's a scaling factor, and so whatever minimizes sigma times this minimizes that thing too. So effectively, it's the exact same thing as just minimizing this squared loss. Okay, so this is kind of nice because now we have another way of interpreting what we're doing when we're doing this least squares. What we're doing is we're maximizing the probability of observing the data under this Gaussian model. Of course, in some sense, this is kind of unsatisfying too, because this is a technique called maximum likelihood estimation. This function here is called the likelihood function. And we usually do it, this full function here is actually a function of theta. That's the likelihood of theta. I'm taking theta to maximize the likelihood. But it's also sort of unsatisfying because really we just went from picking a loss function to now choosing a distribution, right? Why did we choose Gaussian random variables here? If not for the fact that they actually lead to a nice optimization problem in the end, much like why we chose these squares. But there are cases where it's reasonable for sort of theoretical or empirical reasons to actually choose a Gaussian distribution. You can look at data, see if it follows a Gaussian distribution approximately, try to verify that empirically, and that can give you more confidence that both this is a loss function we should be using a Gaussian model here, therefore we should be using least squares loss, and it also can sort of tell you that not only do we now have a not only can we solve the data, but we also have a probabilistic model that tells us kind of the expected range of values for each new input, right? Because now for a new input xi, you actually have a distribution over possible y's, and that can kind of tell you the expected uncertainty, the expected range of those outputs. You can do the same. I'm almost out of time, so I just want to mention briefly, the same goes for logistic regression here. You can essentially define a probability model much like that one for binary random variables. So you can define probability of y given x as this logistic function here. So if you plug in either +1 or -1 to y, this would give you a probability of it being the +1 or -1. Though this is the same function we use for the neural network, actually, neural networks typically are not using this as a probability function. They're just using it as a function that has some nice nonlinear properties. Here we're really treating it as a probability. And the exact same thing happens where if you set up the maximum likelihood estimation task, you get exactly this logistic loss function that we saw from the last lecture. So I won't dwell on that too much, but essentially the exact same thing here happens. You define a certain probabilistic model for these binary random variables. This is a classification task, now a binary classification task. You solve the maximum likelihood estimation problem, and what you get out is the logistic loss function. So if you believe that probabilistic model up there, then the logistic loss function is a good one to optimize. Okay, that was pretty fast there, so I apologize if you hadn't seen that before. It's a little bit kind of quick the first time, but it's really the exact same thing. The idea is we have a probabilistic model. We're going to pick parameters to maximize the likelihood of observing the data that we saw under that model, and what pops out is exactly the logistic loss function. That's the oscillator problem you get in the end. And by the way, just like with linear regression, we can now interpret the predictions of our model as probabilities, rather than just numbers that the bigger they are, the more certain we are that it's +1, the smaller they are, the more certain we are that it's -1. This kind of gives a sort of quantifies that. All right, I actually will probably defer questions till see me in the break, because I want to mention one more thing, which is about evaluating algorithms. So far, what I've talked about, we've talked very briefly about how do you go about picking parameters. I think this is a question that a lot of people ask. How do you pick the k for k-means? How do you pick the regularization parameter, lambda, when you're doing classification and regression? And yesterday, Amanda also talked a lot about how you pick, if you have many hyperparameters, how do you pick between them? Okay, right? So if you have a lot of different hyperparameters that kind of govern your algorithm, how do you pick the best ones? And what's going to be the best error, say? And here's a very common approach, right? Remember, I told you before the way you can do this, the way you can pick, lambda or k or whatever, is by doing this division of your data into a training set and a validation set. All right, so you have your whole training data, say this. Say we'll use 20% or 30%, say, we'll use validation and the rest we'll use training. So just like on the graphs I showed you yesterday, you find the model parameters based upon this, and then evaluate the error, the loss, based upon this held out set you did not train upon. And maybe you then use this validation error to pick, say, your value of lambda. Okay? Now, a common mistake, well, it's actually not that common anymore, but a mistake that you should never make is to do that, to run your machine learning algorithm here, to pick the best value of lambda, and then you report in your paper that you write up, you report the validation loss that you got. So why is that a bad idea? Any guesses why that's a really bad thing to do? Yeah?
Well, the lambda is basically being trained in a validation set.
Yeah. So effectively, we're training our theta, you can think of training our theta parameters from this set, but we're really picking our lambda parameter based upon this, and it's sort of the best possible one you could find. This is still training data. This is not indicative of new held out data. You are using it to actually choose the best value possible. You are effectively training on your held out set. It's just you're not training your theta parameter, you're training your hyperparameter, your lambda, or whatever parameters you use for your Bayesian optimizer. This was actually a very common thing for a while. People would just sort of find the best parameters here and report what they got as the error. The correct way to do this is to actually separate out an additional testing set. So you take your data, you actually call this a testing set, And in the land of big data, the fact that you're throwing away all this data here is less of an issue, right? Because you guys have so much data. So it's probably okay to use them for testing. You can also do things like I was talking about, where you send this online, so you incorporate more training data as you go. But you take your data set, and divide the testing on a training set, and then you can subdivide this again, the training and validation. And use this one, do all your training and model building on this data, and then do this one only when you're finally done and ready to test. And so the procedure essentially is break the data into training and testing sets, example 70-30, break the training set into training and validation sets, choose your hyperparameters based upon this, do all your learning here. Test once and only once on your testing set, right? So you test any more than once, you are violating the principles of machine learning and the principles of statistics here. And if it isn't good, then you throw away your results and scrap the paper, and then it's just a negative result. You never look at it again. Of course, it doesn't actually happen, right? What happens is that in practice, people often do effectively overfit the testing sets by more or less, if their algorithm does not work, let's try a new algorithm. And there's often some leakage in terms of people effectively letting performance of the testing set influence the type of algorithms they pick, the type of design they do, because you want that good performance when you're writing a paper, right? You want to make sure you get a good result in testing set. So you have to be careful with this. But I think also in the realm of big data, we have the ability to always pick new testing sets, to always sort of, do our training. It doesn't work on this testing set, well, we throw this testing set away, pick a new one randomly, right? Because we don't want to bias ourselves towards good performance on any one set. We want to really evaluate it differently. So this is a little sort of, one quick note here about how you evaluate your algorithms. When you do your reporting, make sure to do this kind of splits like this, and then don't, as much as you can, try not to overfit the testing set. So even the best people, I think, do that a little bit sometimes. Okay, well that is the end of this lecture, and I think next up is Alex. Next up, you are.
Okay, I thought Nando.
Oh, it's Nando next up. Okay, Nando is. Okay, anyway.
Well, that was 5 minutes.
I'm very happy that I took my start course. Yeah, you don't know.
Yes.
Oh, it was you who dropped out.
No, I didn't know. It's all good, but yeah, it's all good.
So good. So that's a good thing. I know, and then talking to someone who took the course, they drop out, and doing zero and then work.
Test 1, 2, 3. Am I too noisy? Am I too quiet?
Hang on one second. Try again.
Okay, test 1, 2, 3. Who wants me to use the microphone and use the amplifier? Okay. Who doesn't want me to use the microphone? Okay, so who doesn't want me to use the microphone? Okay, so I think nobody really cares. Because we got 2 hands each. I'm assuming that a lot of people who didn't hear the question, who doesn't want me to use the microphone, so I'm just going to use both. Kind of weird, but yeah.
Oh.
Tico?
Yeah.
What did I do? Do you know whether we have another screen adapter? Because it's just the display.
Oh, single detector. Oh, okay. Alex? Are you still going on?
What?
Are you still going?
Well, I mean, we're basically trying to get interaction with the latest.
Do you have it in your bag? So let me just go get it.
Well, I mean, apparently, yeah. Okay, so today we're going to get a little bit more specific. Not too many equations shall be harmed today either. Tomorrow it'll get a lot more equation heavy. What I'm going to do okay, are we recording?
Yep.
Cool. Okay. So today what I'm going to do is I'm going to give you an idea of what's in the parameter server, and then we'll start looking at how to actually use this, for instance, in the context of graphical models. So Moon will give you a lot more details about that later in the afternoon, which is also why I'm going to skip over a lot of details in the context of logistic regression, simply because he's probably going to pick it up in the afternoon anyway, and you'll actually get to play with that system. So this is really collaboration between a lot of people, but the major credits really go to Moon. He did most of the software engineering. Let's start with a bit of background. So yesterday we already talked about here that we have lots of data. You have terabytes of data, thousands of computers, billions of parameters, and the machines fail. And you end up sharing a cluster because usually you don't just get a cluster of 1,000, 2,000 machines on your own because, well, it's just expensive. And you do care about the performance. So, for instance, you might have front-end serving machines, which in real time might want to adapt to whatever you're doing. You want to have real-time response. So this is a little bit more hostile than your university cluster. This is something to keep in mind, and some of the design decisions were really heavily for that. So let me show you the general parallel algorithm template that we found actually works very well, and this has become known as the parameter server. This idea actually, okay, I first got this idea by watching a talk about artificial intelligence, where people used to integrate various systems by the means of what they call the blackboard. And so basically what would happen is that various inference subsystems would perform the inference, and they would write their insights about various pieces onto, so to say, a logical blackboard, where other algorithms would go and pick it up from, and then perform their own updates, and then they would write that data back onto the blackboard. And this would just continue. So when we then had to actually, scale things beyond a single multi-core machine, I basically thought, okay, let's actually try a similar template there. And that's turned out to be amazingly powerful. The reason why we didn't go for anything way more fancier than that is because you have essentially this trade-off between wanting to build something very general that's very powerful and constraining things down to some very narrow API to some very narrow set of capabilities for which you can then optimize a lot. Because in the end of you have a limited amount of developer resources, and if you want to do something very general that's also very powerful, then you need a lot of people working on it. And yeah, we didn't. So this actually turned out to be an advantage in the end. So what basically happens is that, okay, so this is essentially a caricature of this blackboard. And don't worry about which machines and how many machines and so on we have for the moment just yet. I'll get to that in a moment. So basically, you have the equivalent of a server, so that acts as a blackboard, which has a consensus view of some sort of the parameters that you're dealing with. So these could be, for instance, the model parameters in your linear classifier. They could be the language model for your topic model. They could be the means and covariances for your mixture of Gaussians. And the server essentially has this consensus view of the entire world. Right now, assume that the server has infinite bandwidth and infinite memory. We'll deal with that issue in a moment. Of it hang a lot of clients. Those clients have a subset of the data, and they have basically a partial view of what's going on. And that partial view may be perfectly sufficient to actually deal with the data. So for instance, if you had one set of machines that had English documents, another one that had Spanish, and a third one that had French documents, then the machines holding the English data would probably not need to know very much about what the language model for Spanish and French is like. So they would only need a very narrow view, and they would only need to basically communicate to the English and French machines in the context of, well, words that possibly occur in more than one place. Now, you might actually ask, well, why on earth do we actually need the central server? After all, the clients could just talk to each other. The problem is that if you have that, then you will end up with a complete graph. And that has a number of edges that scale quadratically in the number of clients. By adding an extra hop here, basically, if I want to talk from here to there, I have to go through the server. I basically double the number of steps, but I've reduced the number of edges in that graph from order n squared to order n. So that's really important. Why having a central server simplifies a lot of the communications mechanism, and it also simplifies a lot of the design. So there are people who've tried to design essentially complete graph type communications patterns. So they have, for instance, gossip type algorithms and so on. But actually, that's not the brightest idea in this context, because you actually do have a fair amount of control over your server center. So you don't need gossip type algorithms, which are really good for highly faulty communications. But you usually have a reasonably decent type of hardware infrastructure. Yes, it can fail, but it's not like having 1,000 machines spread all over the internet. So what that basically means is that you need 3 different key pieces in order to make your algorithm distribute over several machines. You need a reconciliation protocol. So basically what that means is, if 2 local machines have different values, how do I actually reconcile the fact that they do have different values? Secondly, I need a synchronization schedule. And that basically means that you need to predefine whether each machine just asynchronously keeps on hammering the data to the server and gets things back, more hot-wild style scenario, or where you have episodes where each machine goes and computes, let's say, parts of the gradient, like what Tico mentioned with gradient descent. I could just compute parts of the gradient on each of the machines. Then the server gets this, it does something interesting with it, and then it sends it back. And you also need to decide how to distribute the load. So on the client, a natural thing would be, for instance, if they're all equally powerful, each gets a fraction of the data. But then you also need to worry about things like, well, what if a client dies? Which other clients get which piece of the work? And you can immediately see that there are certain benefits, for instance, in keeping all the French documents among the French machines, so to say. there are actually some arguments when you might want to, redistribute uniformly, but that's just some of the details. So by now, I think there are probably 6 or 7 industrial implementations of the parameter server in pretty much every major internet company with different flavors. I'm going to show you one version that we just, at least for the, we have a beta version out right now, and that I believe actually addresses a whole bunch of the issues that maybe some of the others may not quite address in the same way. So let me, without much ado, show you the architecture. So remember, I told you that that the server, has infinite memory and has infinite network. Well, of course, you can't really have that. What you do is you basically have multiple servers, each of which take a slice of the parameters and therefore also communicate only with the clients for that slice of the parameters. And this way, you can actually get perfectly linear scaling. So that's kind of nice. And you need a server manager, which basically ensures that if one of the servers dies, another machine is started, and that things are properly replicated. I'll get to the replication issue in a moment, but basically there is a job which basically just makes sure that you don't lose all of your servers, and if you lose some, that the other servers are instructed what to do. So think of this very similar to the basically master controller in the Google file system. Furthermore, you have groups of worker nodes. So in pretty much everything else, people assume that you only have one group of worker nodes, but in essence what you could have is that you have a front-end serving system, which is serving ads. And at the same time, you have a back-end system, which is updating the click probabilities for your computational advertising system, and they both operate on the same set of parameters. So this is why you actually want to have several groups, which may do very different things on a partially shared set of parameters. Now, each of those groups basically consists of worker nodes that work off the training data, and then you have a task scheduler here, which basically determines what those worker nodes are supposed to do at which time. So that part looks awfully similar, for instance, to what we discussed yesterday about Spark, which also has basically a job controller for the clients and then hands out tasks, except that we have slightly different capabilities and consistency models than Spark. But it's essentially that same flavor of task controllers that really simplifies things a lot. So let's dive into a little bit more details. So the communication pattern is like so. So basically, since we don't only have a single server with multiple ones, we basically get a complete hypertext graph. So all clients can potentially talk to all servers, and all servers will potentially talk to all clients. And I've just zoomed into the case of a particular client, which basically talks to all the servers, and a particular server which basically synchronizes all the clients. So the obvious thing that you should be worried about when you see this is, well, those machines sit in a real server center, and isn't it the case that, well, basically you have a real network infrastructure, and then maybe you have oversubscription, so basically you might have a switch in each rack, and then you have all the switches ganged up. Well, aren't we ignoring something? That actually used to be the case in the, so to say, good old times. By now, fortunately, most modern server centers have very interesting network infrastructure, which pretty much makes the entire system behave as if it was just, everything was just on one switch. So if you want to know more about that, you should, for instance, look at the tutorials of David Maltz and look at things like butterfly networks, cloth networks, that type of infrastructure. And that pretty much obviates the entire issue of not everything sitting on the same switch. So that's why that abstraction here that we've made is actually pretty accurate in terms of what's going on in the server center. So basically, consider that a solved problem on Amazon, on the Azure cloud, or at Google. Okay. So now the obvious thing is, well, how do we actually distribute the keys between different machines, and how do we make sure that actually I can, recover things? So an obvious strategy that you could do, and we committed that crime several times, and until we realized that we were doing something amazingly stupid, and mind you, several people read our papers and they then did the same not so intelligent thing that we first started out with, and I must admit I copied this idea from MemCached. By the way, who knows here what MemCached is? Okay, it's about 10%. So MemCached is a really nice distributed high availability key value store. And basically it does three things. You can send it a key value set, and you can query that, and you can delete it. That's pretty much all it is. And since those keys are entirely arbitrary, basically what you do is you use a uniform distribution mechanism to distribute keys over machines. So what I do is I take a hash function. Who knows what a hash function is? Great. Okay, so it's basically like a random number generator, except that each time you feed it the same argument, it gives you the same output. And that's all we'll talk about here in this context. What you do is you basically, let's say I have a machine pool of 1,000 machines. I compute the hash of the particular key and the machine ID for all the machine IDs. Okay, don't worry about this being really slow, but let's just conceptually do that. So this gives me a random number for each machine. And then I go and pick the machine with the smallest hash value to be the owner of a particular key. So this way, I get a uniform distribution of keys over machines, which is great, right? So if I now have, let's say, for instance, words in a topic model that I want to distribute over servers, that makes it very easy because it's all uniformly distributed. So that's basically what's happening here. Now, if I was to add another server to it, well, that would be very easy because all that happens is that only for a fraction of 1 over s, where s is the number of servers, the keys will get reassigned. So the advantage is that I have perfect load balancing, and furthermore, I also have a minimum number of keys that I would end up moving between machines if I was to add one, and ditto if I was to lose a machine. MemCached does this, and it does it very well, and for their purpose, that's pretty much the best thing you can do. However, the problem is that MemCached itself, for instance, doesn't do anything like version writes. So there's the issue of basically, let's say I have 2 machines and they are a little bit out of sync, and basically who got to write first. So think of it like in a version control system, if 2 people check in their stuff at the same time, and it doesn't actually keep track of version numbers, you can end up deleting each other's code. And that's not so great. So there are things like basically vector clocks that can deal with that, but it's very expensive to do. So if you want to know more about the approximations that people make, there's, for instance, the Dynamo paper from Amazon. So just Google Dynamo Amazon, and you will see the paper that describes their distributed key value store, where they make various approximations to keep that versioning at bay. But there's a much, much bigger problem lurking underneath, which is if I want to, for instance, have a client talk to a particular server and say, well, let's just synchronize all the parameters that we share. And this is extremely hard to do. It's extremely hard to do because we use this hash function. And this hash function randomly assigns keys to servers. So I pretty much have to keep a list of all the keys that go to a particular server, stored on the client. And then I have to traverse these. So this is computationally very, very expensive. And fortunately, there's a perfectly good solution how to fix this. And that's basically to use a distributed hash table. So this, for instance, also what peer-to-peer networks use. The specific version that we use is probably most similar to what's called pastry. Core. So actually, core is probably the most approximate way. So what you do is you again take all of your keys, you compute a hash, and so now you can actually arrange them in a ring, because the hash function will go from 1 to, let's say, 2 to the 32, and then it wraps around again, right? So we can just close that line and we get the nice ring. So each key sits somewhere on this ring. Now the next thing that I'm going to do is I'm going to insert the servers also on this ring. So for instance, I take the IP number of the server and I compute the hash and it sits somewhere. And actually, you probably already saw here that each server has several edges into that ring. And that has to do with the fact that if I want to insert each server only once, I will get a very uneven load balancing. Turns out you need to insert each server log number of times. Okay, good. And then what happens is that, okay, so each server sits there, and it will be responsible for the segment between that machine and the next insertion one level up. So basically, each server now owns a segment of that ring. This makes it very easy to reason about which keys a particular server owns. Because all I need to know is where in my hash ring the keys are, and then I know exactly that entire segment is owned by a particular server. Right? So like the red segment is owned by server 1, and the blue segment is owned by server 3. So that's really great, because now what I can do is I can have a one-to-one mapping between my internal memory layout on the clients and a range partitioning that tells me which server I end up talking to, and I still get all the load balancing properties that I had otherwise. There's another really cool thing that I get fairly immediately, and that's key replication. Because basically what I can do is I can just specify the next machine on that ring to take care of keys if one machine should fail. So let's first actually look at what happens if one machine should fail. Let's say we failed server number 1. Well, in that case, what happens is that now server number 3 will end up having to take responsibility for that blue segment and the red segment, because server number 1 is gone, right? So all that happens is now that the segments just coalesce, and I just end up sending a large block to that machine. Now, what I can do is I can basically make server number 3 already get a copy of the data from server number 1. So let me show that here. I know that looks like a spinning washing machine, but basically what happens is that always the next machine on the ring gets a copy, likewise here, likewise there. Now, since this is very awkward to view, I'll show it to you in a moment, everything flattened out. But basically, okay, so there we go. So I basically have a server which owns the copy, let's say that blue segment, and then servers 2 and 3, which are basically subsequent servers on that ring, will get a copy of it. So here, server 2 owns segment B, and then servers 3 and 4 get a copy. And the same here and the same there. Right. So now let's see what happens if a machine should fail. So let's kill server 3. Server 3 is dead. So now, okay, what happens to the blue segment? Well, nothing really, because server 1 is still serving it, and all the clients will happily continue talking to server number 1. What happens to the red segment? Well, nothing really either, because server 2 is still serving it and everything's good. Likewise, well, segment D, so the green segment, is also just completely fine, because nothing really happened. The only segment that I really need to worry about is segment C, because that now has just lost its primary server. However, if you look at it, there are machines 4 and 5 that have essentially a hot standby copy of that segment. So now all I have to do is basically just tell the system that, by the way, server 4 is now responsible for this. And all I have to do is just pull the markers from the ring that we had before, right, out of the mapping table. So basically all I need to do is I just have to tell all the clients, by the way, server number 3 just died. And now everybody can immediately reason about which machine is going to be responsible for things. So I don't really need to have a global mapping table of which key goes where. All I need to do is just maintain liveness information about, clients and servers. On top of that, while I obviously will try to do this proactively, if a client tries to talk to the server and the server is dead, well, it'll know immediately, well, that server is down, and it will immediately be able to reason about which machine to talk to next, which is kind of nice. So now server 3 is dead. Let's see what we can actually do to repair this. Because, okay, while I've survived losing one machine, and as you can see, I have 2 replicas of the original, so that means I can, deal with 2 machines died at any given time. If I also lose a 3rd machine, my system would, break. So let's see how we can actually deal with this. So we need to repair the entire layout. Let's look at the simple things first. So basically, for the blue segments, all we need to do is we just need to realize, well, okay, the next machine up is machine number 4, so we just make a copy. And this can go from the, owner of that segment to, the tail, likewise here. And now we only need to deal with, what happens to the yellow segment. Actually, what happens is we simply say, well, hey, the segments are merged, so this now becomes part of the larger green segment. For that, I don't actually have to do any copying whatsoever. This is just a logical operation where I just manipulate a pointer. The network traffic occurs. And then I make a partial copy of this bit down here. So what you can see is that the entire repair operation cost us only as much network traffic as what that one died machine held, which is kind of nice. So you don't really have to do any other expensive reshuffling. All you do is just, well, if your server held 16 gigabytes of parameters, you get 16 gigabytes of network traffic. That's about as good as it gets. Okay. Now the last thing that you need to do is you need to worry about what happens when we actually recover. Because at some point server 3 comes back, or let's say if you keep on losing machines, you want to actually keep on adding machines back in, such that the total number of machines is the same. Well, again, it's very easy. What you do is you pre-copy server content to a new candidate. And in the case of the blue and the red segment, that's kind of easy, right? Because these are not really live segments that are receiving updates, so we don't really have to worry very much. It's only really interesting in the context of the green segment, right? So in this case, because what's happening is this server keeps on getting updates from its clients, and the numbers change, and everything keeps on changing. And at the same time, at some point, you need to switch over to a new server, right? And that's not trivial, because suppose I received 1 gigabyte of data from the clients, and at the same time, I only managed to blast out 1 gigabyte of data to the new server. Well, then basically I'm as much out of sync, and I need to send as much of the diff along, and you will never be able to overcome that backlog. But here's also where, quite conveniently, the number of virtual servers per real server helps you. So let's say I have 10 virtual servers on a real server. So that means each virtual server receives only 1/10 of the data. So now, instead of receiving 1 gigabyte of incoming data, I only get 100 megabytes of incoming data for that server. At the same time, I'm using all my outgoing bandwidth to update the new machine. So at that point, I'm basically, so what happens is you can immediately see it basically takes me only 1/100th of the time, because it's 1k over 4k squared, to set up that new server as what the data is coming in, because I'm winning at both ends. And what this does, it basically means that by having more, by having like 10 or 16 virtual servers, I can very quickly pre-copy all the relevant data to the new machine. And they will only have a very, very tiny stale backlog that I need to send in the end. And that means that actually I will have only very minuscule downtime in the order of milliseconds between when the old server is still serving things and when the new server takes over. And that's kind of tolerable. So what I described to you is a much more effective way of distributing parameters over machines, how to recover. So the idea is, it's ridiculously easy, right? And essentially, we've stolen and borrowed from a lot of systems papers to do this properly. But it's a huge difference between that type of layout and what pretty much everybody else has been doing and is doing. And it's really just, rediscovering a lot of systems tricks in machine learning. Any questions so far?
So according to the bipartite graph, it looks like the recovery is initiated by a client who discovered that the server is failed, the client doesn't get any response. So is it initiated by the client to copy all these things and do the recovery?
Okay, so the question was, is it the client that discovers that a server has failed, and so is it the client that actually decides what happens? You could design a system this way, and it will probably be a little bit difficult to manage the fact that maybe several clients at the same time decide to do various repairs. What we did instead is we actually have a master controller, which basically just keeps track of which machine is live. It doesn't have to do anything particularly laborious and a lot of computational. It just needs to actually keep track of who's live. What you can do, for instance, is then that the client comes screaming to that master controller. It says, well, server number 42 has died. And then the master controller does the things. You could also implement it in such a way that, because the servers need to talk to each other anyway for replicas, right? And so what you could do is you could have a server just discovering that, well, this replica, whatever, has died. You can design a corresponding protocol as well. The advantage of that protocol is that you don't need that master control, which has certain advantages in terms of resilience. But it actually makes the entire systems design a lot harder. So in the end, we cut corners and basically went with the master controller instead, and we just have to make sure that the master controller has sufficiently high availability. So it's, there's a trade-off between to what lengths you want to go in terms of resilience and how much, coding you want to spend on it. But it's a very good question. Any other questions? Okay, good. So then the next thing to actually look at is, well, how do those machines communicate with each other? And then, we'll get to a practical example, logistic regression. So the first thing that we do is this was actually a guiding design principle overall in the parameter server. Whenever somebody else had written a piece of code that we could use and that was being supported by them in active development, we would not try to write our own. This is quite different from some other basically systems where basically people try to have something that's very self-contained, which makes it easier to deploy because you don't need all the dependencies. But it's also a lot more work if you have to build everything from scratch. So we basically went with 0MQ for messages, and we use Google protocol buffers for serializations. And well, what you then actually need to do is, in the context of communication, you need to make sure you're sending large enough messages over the network, and you need to avoid a large metadata overhead. Okay. So let me explain a little bit of what happens here. So when you send, let's say, a scalar from one machine to another. That scalar needs to be packaged up in some data format, which tells the receiving machine that it's receiving a scalar. So you need at least some extra overhead to what's called serialize that amount of data. Now, when this actually goes over the wire, you basically need to create an entire, TCP/IP packet for this, which is then sent to another machine. And so basically, you end up, rather than sending a scalar, which might be 4 bytes, maybe we can turn our phones off. I know it's nice music, but thank you. So yeah, okay. So basically, the entire packet overhead is sufficiently large that first of all, it actually takes you time to initiate the communication. You have the overhead, and basically you end up paying between 10 and 100 times of what you should be doing for sending just a scalar if I just send a scalar at once. So what you want to do is you basically want to send in bulk. And you want to compress out things that are not really necessary. So aggregation is exactly the reason why I was very much interested in being able to know beforehand what entire ranges of parameters are that go to a specific machine from a specific client. The overhead is also there insofar as we basically have, well, all the keys that go with the values. So for instance, if a particular client just has 10 different keys, and it never sends anything else but those 10 different keys. Let's say key 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Of course, they'll have some fancy hash ID, but it's basically only 10 of them. Then I don't actually need to send the second time those keys along. All I need to say is, well, hey, it's the same keys as last time. And that information I can encode much more compactly than actually sending the keys. Furthermore, in terms of the values that haven't really changed very much, maybe I don't need to send them either. So I can maybe just send, well, the meaningful values, and then I pad the rest with no change, no change, no change. Or maybe it's a change that's not big enough to actually make it worthwhile sending. And using those two ideas, I can gain substantial bandwidth over the naive thing. Okay, so let's look at what happens. The first thing actually that happens is when we send copies from the client to the server, and the server starts aggregating terms. And then maybe it sends out the replica and so on. So then actually what it does is it tries to pre-aggregate several updates that it might have received from several clients before it actually goes and sends those copies on to the replicas. And so this way, I have to do a lot less work to keep the replicas up to date. It also means that if I have, for instance, 2 workers here, which both send something to server 1, which then wants to do a replica, well, those workers will only get the act that actually the data was, all committed once it gets aggregated here and it's in. But what you can see immediately here is we're just effectively doubling our bandwidth to server 2 by aggregating things here and then sending it on. So this should look very familiar if you saw the Google file system chunk server updates, right? We basically wrote into the Google file system writes into one chunk server, which then replicates on. Same thing here. Now, the other thing is that, as I already mentioned, sending key value pairs is inefficient. So what you do is you only send the values, and you cache the key list. And if the key list is the same as before, well, I don't have to send it again. Furthermore, if I perform optimization, and I have a bunch of gradients that are tiny, then maybe I don't have to send them. So what I do is I basically only send the large gradients. Furthermore, And we saw that, for instance, with SVMs. So there wasn't actually much background on optimization so far, but basically what you can do is you can check for each instance how close to optimally solve that instance is. And there's something called a courage-Kuntaka condition, which tells you how close to optimality you are. So what you can do is you can choose basically not to send updates for parameters that are close to optimality. So gradients are one way of telling how close you are. Looking at the Kuntaka conditions are another way of looking at that. So basically all this means is that I'm filtering out a lot of data before I'm really sending things to compress my messages. So to give you a bit of an idea of how much of a difference this makes, so this is a semi-log plot. So this is basically orders of magnitude 10 to the 2. That's 100% of all the parameters that we're sending. And what you can see is that after 10, 20 iterations, we are really only sending a very small percentage, like 4% or so, of all the parameters through. So that, in combination with the key compression, gives you probably about a 40, 50-fold speed up over the naive thing of sending everything over the wire. Now, there are still a lot of further things that you can do. You can basically design other filters that are based on randomized algorithms. We're still exploring that area quite a bit, but suffice it to say, by actually being very choosy about what data to send over the wire, you can get substantial speed-ups quite effectively. A couple of other things. This is again in the context of, well, don't write your own if something good exists. We use eigen3 as data types. That covers a lot of cases, doesn't cover some others, and we're at the moment looking at some other data representations. But it basically covers density sparse vectors. And then you push and you pull, and when you perform those, you can actually give it a flag of exactly what these updates mean. But ultimately, what you'll really have to do is you will have to, for a specific optimization inference algorithm, implement quite possibly what the updates mean on the server. So for instance, if you have a proximal gradient update, and I'll get to that in a moment, then actually this means that I update the parameters and I have to perform shrinkage again if I have something like a distributed Gibbs sample, then maybe I only need to update the counts. But basically, the meaning of those updates can change quite a bit between different algorithms, and you need to implement what they mean. But the overall functionality is there that you just say, well, push and pull. Yeah, okay, I'm probably going to skip that. Details on exactly what the various bits and pieces are, because Mu is actually going to talk about that in a lot more detail anyway. An important design decision that we made is that, well, when, let's say, a client decides to send some parameters to the server, the time between it decides to send things to the server and the time it actually gets things sent off, because this is all asynchronous, it may take a little bit depending on how full our queue is. And you could do two things. You could either make a copy of the payload that's supposed to be sent to the server at the time when you generate that message. There's an advantage to that, because it basically means that at that point, when it then gets sent to the server, the client doesn't have, or it gets queued up, the client doesn't have to worry about anything else and doesn't have to worry about overwriting things and so on. But the problem is that the data may get quite stale if the delay is too long. So what we do is, by default, we do not make a copy on queue. If you want to make a copy, you have to do it yourself. So this allows you to design hot-wild-style algorithms that can very easily tolerate the fact that, well, basically whatever gets sent is whatever is the latest and greatest at that time. But if you want to be, more conservative, well, you actually have to add that mechanism. So this was a conscious design decision, and you just have to be careful about it when you implement things. A couple of other things that we did, I think this is actually very pretty. So often people argue about various consistency models between how clients process data. So for instance, you could have a fully sequential model where you process one and you process the next and the next and the next and the next. And effectively, this is like a chain graph where basically one thing just depends on the next thing, depends on the next thing. And what you want to do is you want to make sure that all the previous terms are up to date before you move to the next. So for instance, a iterative batch subgradient descent algorithm would be of that form where the next gradient update depends on the previous value, and you keep on doing this. Eventual consistency is pretty much the opposite, where I don't really care about what anybody else does, and I just do my own thing. That's basically graph number B, and it has no edges. You could also do something like bounded delay, where you say, well, each of those updates needs to be at least as precious. Let's say, for instance, here 2 steps out of sync, or like what's there. So if you design that graph, you are, not quite as constrained as sequential consistency, but also more constrained than eventual. And you can actually design a lot of different dependency and task graphs. So this is a bit different from the data flow consistency graphs that we saw yesterday when we looked at Triad and S4. Here it's actually consistency in terms of state delay. So that's a rather different concept from what pretty much everybody else does in systems design. The good thing is, once you actually specify this graph, you can just work off how various work packets are sent out to the clients. And so we have a corresponding task processing engine both on the client. So if I can download the entire dependency graph onto the client right away, it'll just process it. But I can also inject new pieces from the task controller. What this also means is that as the optimization algorithm proceeds, I can change that dependency on the fly. So for instance, initially maybe I require very tight consistency, and as my optimization algorithm degrades more and more into averaging, I really don't care very much about very tight consistency. So I can relax that eventually. So what this means is I can design a large class of much more flexible algorithms, and I don't have to get into this essentially fight of the, who believes in sequential versus eventual versus asynchronous versus in whatever. You just code up whatever dependency you want, and that's good there. Okay. So that's quite a different approach to pretty much everybody else doing programming. Any questions so far? Because if not, then we'll actually dive right into models, and I think all we'll get to do today is logistic regression. So let's recall where this actually came from. So, if you,
Sorry, I have a question about the previous slides.
Okay.
Back into the, when you're doing like segmentation.
Segmentation?
Yeah, there.
Here. Oh, okay. So
I'm just wondering about section E. Why are we keeping like only 2 duplicate copies of the?
Because I ran out of space here. So basically, this continues on. It's just that here at some point the slide ends. But basically, if I really truly only had 6 servers like here, then server 1 would also take a copy.
Okay.
Yes. I was just being lazy, but it wraps around. Yes.
Okay.
Any other questions about this? Yep.
Since you're on the slide, why did you choose to merge the yellow and the green segments? You could have just left the. Was there a particular reason why you chose to do that when C failed?
Well, because basically somebody has to take care of the poor yellow segment, right?
Correct. So
And
you could have just moved the yellow segment, let's say, to 2.
I could have moved it to 2. That's correct. It's a very good question, actually. So, well, if I wanted to move it to 2, something very horrible would have happened. During the time when I moved this yellow segment to 2, nobody would have been serving the yellow segment. But I want to be able to just, basically, change one bit of information, namely server 3 is dead, and just be able to carry on serving content right away. So it's really for the hot failover that if you start preparing for the repair after the failure, it takes you some time. Whereas if everything is already ready, all you have to do is just switch over and everything's good. Basically like a hot standby. So that's the main reason why we don't do that. But yes, after you repair, that's exactly what happens. Now, there are a couple of obvious things that you can do. So you can see that here, for instance, the segments don't exactly have the same length. You can go to all sorts of tricks to balance this, and you can also deal with the fact that, for instance, you have machines with possibly different capacity, so they get smaller or larger segments. So one way of doing this is, for instance, adding or removing virtual servers per machine. The other immediate thing that should be obvious from this here is that you can dynamically rescale the load of your server. So let's say you're a scrappy startup and you may be able to afford only maybe 20 servers, and your startup does really well and you get a lot of more requests. You can dynamically just keep on adding in more machines, which will then partition that ring further. And this is no different than just the repair that I described. Because once I'm in this situation here, right, that's a perfectly valid layout. So inserting server number 3 is just like adding another machine to an existing running pool. So the nice thing is that this way I can add machines while it's running, remove them. I can actually even migrate my entire system to a new set of machines by just killing the old and adding the new. So that's what makes it very flexible, because you can do that while it's actually a full production system. The only thing where this would fail miserably here is if I was to lose more than 3 machines. That must never happen. So what you do in that case is you actually checkpoint the current set of keys occasionally to, well, more persistent storage, such that if you lose a lot of machines at once, well, you just restart from there. There's really very little you can do, because it gets very expensive if you have a lot of replicas. The other thing to keep in mind is that, sure, you probably want to have that copy here in main memory, but you can write this to disk, at least to an SSD. Because the more replicas I have, the more expensive it is in terms of actual storage. So maybe I keep the first 2 or 3 in memory, and then the next few an SSD, the next one on disk. We have not implemented that yet, but that's a very obvious thing, and if somebody wanted to add that to our parameter server, we'd be delighted to have it. Okay. So now we have about 3 minutes left, and I'll think that will pretty much do for logistic regression, at least, to give you an advanced preview. So remember, you actually care about this to find out whether somebody is stupid enough to click on mesothelioma lawyers. Okay. So let's actually derive the logistic. And we already saw it in the morning, but let me just derive it in a slightly different way. So you may or may not have heard about exponential families, but this is actually going to give us the simplest way of modeling an exponential family. So let's say y is 1 and minus 1, 1 being, the person clicks on the mesothelioma ad, and minus 1 is he doesn't. And so what I can do is I can model p of y, so p of click, given some number t, as being proportional to e to the 1/2 yt. Ignore the 1/2 here, that's just to make the math look pretty afterwards. But basically, what you can see is that if t is large and positive, that means there's a good chance that he will click on the ad, and if it's very negative, there's a good chance he won't. So in other words, y will actually tend to agree with the sign of t. The goal is, in terms of inference, just find t. Okay. Now, of course, this is not a proper probability yet, because right now, if I take this, for y equals 1, and the term for y equals minus 1, adding that up may give me any number. It could be way larger or smaller than 1. Okay, so there's a very simple fix. And just take this and divide it by the sum of, well, e to the 1/2 t, so that's for y equals 1, plus e to the minus 1/2 t. And now comes a slight conceptual, well, it's just a really tiny manipulation. since y equals 1 or minus 1, I can pre-multiply both of those terms with y. Because if y equals 1, nothing happens, right? If y equals minus 1, then this becomes e to the minus 1/2 t, and this becomes e to the yt. The same thing as before, except that the terms swap. But what this allows me to do is I can now divide by e to the 1/2 yt. And I get something that you've seen in the previous hour. 1 over 1 plus e to the minus yt. This is where the logistic regression comes from. Okay? So, once I have this, I can do very simple things. I want to basically find t that correlates with y. And so I might want to find some function f of x. For instance, the kernel that Sigmund mentioned before, maybe just some linear function. And we're mainly going to concern us with linear functions. Or if we do what Fox talked about yesterday, we can have a deep network. But basically, I get, I want to get p of y given x as a function of e to the minus y f of x. Okay. And so to prevent overfitting, I basically invoke Bayes' rule, and I can see that the posterior distribute probability over those functions f, for instance linear functions, is proportional to the prior on f times the likelihood of this function f explaining the data. So basically, for each user that comes along, that might click or not click, I get some probability. And multiply all those terms up. So that's basically p of the data given f times the prior p of f. I would actually need to normalize that. That's why I can only write it proportional. But this is now proportional to p of f given the data. Bayes' rule. Now, of course, I need to specify things in a bit more detail to make progress. So one way, for instance, of going about that is I have to pick a function class, let's say linear functions. I need to pick a prior. And one that we're going to talk a bit about later on, and who is going to talk a bit about that quite a bit more, is a sparsity prior. So that's basically just the one norm on the coefficients. And of course, I have plus a constant here, which just needs to integrate out to 1. But that constant doesn't really matter. And then I need to pick an inference strategy. And what I could do is I could sample. And we're going to see sampling algorithms later on. Or I could simply optimize. Now, the reason why this optimization strategy works really well here is because the posterior probability over the parameters is log concave. That means that it has a unique mode. And we can find that mode by optimization. And here's the optimization problem that arises from it. That particular prior is not the only one. You could pick a lot more. And I think I need about 2 more minutes to finish, and then now we can get over. Here are some other priors that you can use. So the norm squared prior is the red curve here, and I think everybody's seen the quadratic function. I'm not going to compute the derivative height today. So 1/2 WI squared. The blue curve is the absolute value. And that's basically the sparsity prior that we saw before. So what you can see here is that basically it has a non-zero derivative on either side of 0, and that will basically push the coefficients to 0. There's beautiful theory which explains under which conditions you get very nice reconstruction. Or you could do something a little bit more adventurous and use something like log of the coefficient. Well, we have to know the coefficient plus a small constant. And this actually is not convex, as you can see. However, it's still monotonically increasing. And this actually can also be solved by effectively repeatedly invoking an L1 penalty solver. This actually has a couple of very nice reconstruction properties. There's a paper by Stephen Boyd, Larkin, and Candace, and a few others. I mean, that idea has been rediscovered at least 3-4 times, but I think their write-up is probably the best to look it up. Okay. And then, yeah, I guess I'll stop here because otherwise Nando doesn't have enough time. What you do is you can, for instance, for the L1 norm, solve things by what's called a proximal algorithm. So you basically compute a gradient, you perform a gradient update of your parameters, and then you shrink everything back to 0. That's what happens here. So in other words, if the updated parameters are less than epsilon, it's 0. Otherwise, you just, shrink them by epsilon. That's it. Okay. I believe I have to stop right now because otherwise I'm eating into everybody else's time. Any quick questions? No questions? Okay, but then let's stop the video.
I understand the key, but after that,
So those are actually.
yeah.
So you'll notice right. And it's lower than you want that to be like you can just put on the menu button.
Right now,
I don't think anybody has that. It's a little lower than that. We put it down one because and just the shutter button, like halfway down again. If you start and stop, make sure that it's this red button. Yeah, so basically, most of these cameras are like halfway down, and then halfway down. So to get back to the screen,
The RL.
and this shows and this should be on 4K.
right. You know?
I'm not sure. Well, I think that's underestimated. Not quite. Oh, I want to notice is obviously this screen, like the capture screen,
Right.
so people use the platform.
Yes,
I think it's there. Yeah. Well, you can do that. You can actually change it.
What do I change?
Where's the property?
Right there.
Do not run beyond this line.
All right, so let's get started once again. Yesterday I was a bit hurried at the end of my lecture, and I didn't get to answer some of the questions I had promised to answer about high dimensionality and what happens with something too close to the borders. I've given the slides to Zico, and in those slides there's information about that. But essentially, in short, if there are two ways of attacking high dimensionality now in Bayesian optimization. One's via trees, because in trees, as in random forest, like Zico explained this morning, you choose a dimension where to split. So you essentially are picking the relevant dimensions. And so you can attack problems of up to a couple hundred dimensions, as people have done effectively. Frank Hutton has a system that handles about 300 parameters. And they're able to automate software out there. So in particular, there's a very nice paper called AutoEcho where they tune a vector for you. And in particular, they tune 300 parameters. Many functions in high dimensions are also of the nature of some parameters matter more than others. So sometimes you're tuning and some parameters are very critical and another one is not very critical. So in other words, your cost function is fairly constant along a dimension. If that's the case, you can construct randomized algorithms that allow you to essentially do optimization in a lower dimensional embedding of those high dimensional costs. So even though the cost function is high dimensional, only some parameters matter, and it's possible to use randomized algorithms to discover those dimensions efficiently and be able to search in all dimensions. And if you Google for Bayesian optimization billion dimensions, you'll find that there's a paper that solves Bayesian optimization in billion dimensions, provided the true dimensionality is small. There's no magic. If the problem is naturally high dimensional, we have no ways of doing it yet. There's a lot of work to be done there in terms of scaling Bayesian optimization to high dimensions, to high numbers of data, and also in terms of robustifying it with respect to the choice of hyperparameters, if there is elasticity, choices of the boundaries of the decision set that you're going to be searching for hyperparameters and so on. So there's a lot of work to be done there, so if that sort of thing interests you, there's certainly a few PhDs to be written on the topic. All right, so today I'm going to attack a problem that a lot of people have played with, but where it's been much harder to make progress. So where the algorithms are in general not robust, or they don't seem to be robust, and where it's sort of very cool, but in the end, the demos that you'll ever see at the conference are these sort of simple grid worlds, and it's sort of frustrating to get things to work. Zico, by the way, had some of the best RL work that I've seen. Maybe I will add it in some of his lectures. Okay, let's get into it. A decision problem or an RL problem will have the following elements. First, there will be a state, S. Now, a state for an agent is all its percepts, what it sees, what it feels, the temperature sensing, and so on, as well as all its memories. Like, I have a neuron that is firing right now to indicate that I'm here at this particular location, and that I'm standing at this particular location, and so on. And so those memories, those activations that basically give me my current sort of relation in the world to you guys and to everything I sense and do, that's the state. And so coming up with a good representation for state is extremely hard. And mostly people have been using these sort of grid worlds, and obviously that's where the problem is. One of the fundamental problems of RL is being able to say what the state is. And today, what I'm going to try to get to is a nice application of RL that came out last year by a company called DeepMind, where the thing that I like the best in their demo is their representation of state. And it made me so excited to see this new representation of state that I decided to go back and do research here. Now, an agent interacting with the environment acts. So there will be actions A, and these actions will be from some space A, and the actions are only based on different states. Excuse me. You can choose different actions. So think of a state in the sense as a context. When I'm in a particular context, I'm allowed certain actions and so on. The agent is part of an environment. And I will assume that that environment makes the state change. And in particular, that environment will be stochastic, where I'm going to have a noise variable which could depend on the previous action and state. Okay, so your sense the world, you act upon the world changes. And it changes in a deterministic fashion, but it also has unpredictable elements to it, which I encode with epsilon. The agent has as a goal to find a policy, and you should think of a policy as a strategy. And let's assume that we're going to deal with the agent having to make capital T decisions. In that case, the policy will be a sequence of functions where each of these functions maps the state to an action. Okay, so how I make which actions I choose based on the state comes from this function mu, and this function mu will change over time. We say that when such policies change over time, we refer to them as we're going to refer to them as non-stationary policies, as opposed to a stationary policy where the function is the same no matter what time you're deciding. In this case, the decision problem goes up to t steps into the future. And so this is called a finite horizon problem, with the horizon here in particular being capital T. I will use this MATLAB notation or Python notation, whatever you want to call it these days, very common. And so pi naught to t refers to pi naught, pi 1, and so on. Okay, so that's set up. I don't know if I've been optimal in this choice. Let's see. Okay, that's good. So in addition, so the goal is to find a policy, and you find a policy to maximize the expected returns. Or value. I'm going to define that to be this function b pi and I will assume that I'm starting at a random variable s not equal s naught. So this is the value of the variable, and that's going to be an expectation over w. Oops, sorry, epsilon naught to t. The sum from t equals 0 to capital T r Okay, let me parse this equation. What I'm going to do is try to maximize a sum of rewards. So these R's will stand for rewards. And they're the immediate rewards. They're the reward that I get from when in state S, choosing an action according to the policy mu t. And that reward has a stochastic element, which is captured by this epsilon. So there's a cost, there's some objective that I'm trying to optimize, but that objective has some noise to it. So pretty much in machine learning, all problems are of this nature. We're always trying to find the parameters for a certain amount of data that we've seen, but we haven't seen all the data in the universe. So we've seen a finite set of the data, so all our problems are stochastic because of our limited observability of the environment. This expectation is over all the possible uncertainty in the future. So the way to interpret this is it's an expectation with respect to this the distribution of the environment. In particular, how I go. So it's over P of E naught P of E1 given A naught and S naught dot 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 P of ET given AT and ST. Okay, so the expectation is over this sort of every noise variable in the system. We will define the optimal value function starting at state S naught to be the max over this policy of B pi of S naught. So it's basically the value function when you've chosen the best policy over all time steps. Okay, the first way to solve this is something called model-based RL. And so in model-based, we will assume that we know the distribution of that noise. So we know how the world transitions, how the noise depends on AT and ST. We will have essentially someone will give us a simulator, and so we know the function, we know this distribution, and we know the function f. So, for example, in environmental problems, people have spent a lot of time describing how a particular ecosystem might evolve over time, how the trees die and the squirrels come in, etc., etc. So you have these very complex simulation models. So if you want to come up with a policy of how you're going to interact with the environment to harvest resources, then you might as well use one of those simulators and then try to find the best policy to harvest the environment in a sustainable way. So in such cases, we might also want to parameterize the policy. So the policy mu will have some parameters. So you might have that each action will be a function of a policy that has some parameters theta. And so your goal is to come up with the best parameters for this policy. And in particular, it might be often the typical case is that this policy is stationary. So the policy, so delete the t there to indicate that it's the same function no matter what time you are. So what you want to do is just come up with a function that will look at the environment and will tell you what you should do. So one way to do this is to simulate. And when we do simulation, what we're going to do is we're going to sample E naught to t from the probability. I'm just going to write it for short like this, but by that I mean that probability. So you sample E naught first, the system transitions, then you sample E1, the system transitions, you have to compute F, and then you sample E2 and so on. And often it's good to decouple the noise from the deterministic component of the system. That's always a sensible thing to do when building algorithms. Because if you do that, the noise becomes independent, and you don't have to simulate from these very highly correlated distributions. A lot of the techniques that are used in deep learning, in fact, things like if you've heard of dropout, for example, they do that. They try to decouple stochasticity from the deterministic component. Now, assuming that we have drawn several samples of this, and I'm going to use an I to indicate samples, and these I will be from 1 to n. So I'm drawing in samples from n. Now I can approximate my value function. Oh, and I should say using I'm drawing samples from this, but essentially the way I draw samples from this is I pick an E, I draw an initial sample, and then I need to choose, using this policy, I choose the next action. So I draw a sample I, and then my state also comes from using the function f. So given the function f, I can move to the next state. I start with some initial state, and then I move to the next state with the function f. I move to the next a with a, and then that way I'm generating all the basically all the rollouts of a's and s's. Probably I should draw the graph. So if you want to think of it in the type of graph I have is one where I'm transitioning like this, where I have a state variable, transitions to another state variable. I have a deterministic policy parameterized by parameter theta that gives me the action. And then the new state is a function through the function f, and through the probability distribution p, I generate the next state. And then I have a reward, which is a function of these elements here, of 3 stages. This basically encodes epsilon, a, and s. And this is called an influence diagram. Usually we use round circles to indicate random variables, boxes to indicate actions, and then diamonds to indicate rewards. In my construction, I'm making the reward be a function of s, mu, and epsilon. Often, the reward is just a function of s and mu as well. And you could derive everything just by doing it that way. That's not terribly important. I've just picked this notation, and I'm going to stick to that. So this is using mu. So for a particular theta, I can generate all these guys. And once I have the epsilons, because I know f and I know pi, I know every s and I know every a. So I can do the rollout. And so then I can approximate the pi of s naught, and I'm going to put a hat to indicate that it's an approximation, using Monte Carlo samples. And I'm going to sort of emphasize that this is as a function of that parameter theta that I've chosen. And so that will involve these rewards of all my future s's using my parameterized policy. And of course, the noise sum. Okay. So since I can simulate the future, I can simulate the future rewards, and I can just take a Monte Carlo average to get me the value function. Now, my goal is to optimize, to maximize this over theta. And let's assume that I have 10 thetas, and I want to maximize this function. So what algorithm would you guys suggest I use? Pardon?
Bayesian optimization.
Thank you, Bayesian optimization. So you can also do gradients here, but it's actually kind of tricky and it's sort of somewhat unstable. This is a very noisy function. So Bayesian optimization is not only good when you're doing black box and you don't have expressions for derivatives, although if you do have expression for derivatives, you can define a GP over both the function and derivative, and you can do a bit better if you have that information. But it's particularly good because this is expensive. Doing simulations into the future is very expensive. And also, it's noisy. And so when you do finite differences to try to approximate gradients and so on, you often, and even if you try to do it exactly, when there's noise in gradients sometimes can cause instability. So it's one of those cases where if you have just a few parameters, doing exploitation exploration with Bayesian optimization gives you a very easy way of optimizing that. And I will show you some examples where we do use policies that are basically neural networks, and we optimize these functions. Okay, so that's all of it. And I'm thinking that I kind of would like to keep these definitions here and use that board. And I will need help from the organizers to shift the board up. I'm going to erase it in the back here. I'm sure it looks funny. All right, so that's model-based. Next, I'm going to do the model-free. Okay, light. Lighting.
Actually, you have to wait till it cools down before you can change lighting.
Oh,
For
okay.
wonderful reasons. I'll come back in a second.
All right, thank you. All right, where are we? So we've defined the value function with this describe how to do model-based RL. And now we're going to do, so let's revise that we have a model. A lot of problems you don't have a model, but you're acting on the world, you're learning a model as you go. So you're learning a model and you're making decisions at the same time. So we're going to look at another way of doing this called model-free RL. And the phrase, because I actually believe that you actually do end up building models as you go. The value function is a model. So we're going to do, for model-free RL, we're going to derive one of sort of the most fundamental things in reinforcement learning, which is dynamic programming. Slash Bellman updates or Bellman optimality. Now let's assume that we have a value function and that we are at the decision state t. And in particular, let's assume that I have the optimal value function at time t. So start for the optimal. And so we know that that's the max of pi t to capital T of the expectation over all the noise variables, also from stage t to the end, of the reward function. Let's just use the variable k, from k equal t to capital T, and then this would be RT of SD by, mu T of ST, and I'm missing PT. Okay. Instead of writing this all the time, I'm just going to call this whole thing RT in the next few steps. That value function can be distributed. Oh, I missed. So you need to close the square bracket. I think I forgot one bracket up there. That value function, what we're going to do next is we're going to distribute the expectations and the max operators. So we're going to try to take as many inside as possible. So basically, what I'm going to do is this. Right now I have something that's written in this form, and I'm going to change it to something that looks like this. So I compute B plus C, I store it, and then I multiply times A. Dynamic programming, basically. Much of machine learning is about just multiplying numbers that way. The leaf propagation and so on just becomes something. So let's assume that we start by distributing the expectation. So I'm going to write this as the expectation with respect to ET. And then I'm going to break that reward into two rewards, RT, and then a sum from k for t plus 1 2t of rk. And I've moved an expectation inside. And this was the expectation from run out of space, t plus 1 to t. Actually, let me rewrite that so that it's clear. T plus 1 to t, sum over k equal t plus 1 to t of rk. And do stop me if I make any mistakes or if anything is not clear in terms of notation. Oh, pi. Thank you. Still maximizing over the policy. And now I've brought back the fact that it's non-stationary. I'm going to do the more general case, and then if it was stationary, each pi t is just the same mu. Okay. And so currently, the pi that I'm using is as denoted here. It's the sequence of functions. So I'm maximizing finding the best function. So in other words, t plus 1 functions. And I'm taking the expectation over all the uncertainty. So I'm marginalizing, getting rid of all the noise in the system. And here, because RT is not a function of t plus 1, I can take it out of the integral. So I've just distributed it. The other thing I can do now is distribute the max. And so this now is mu t. And the reason why I will be able to distribute the max is because this does not depend on this doesn't depend on pi t plus 1, anything that happens after time t in terms of the policy, so it's just a constant function. And this term here, the reward at time k, as you can see in that expression, will only depend on the first epsilon, which is epsilon t plus 1, so it doesn't depend on epsilon t. So I can now rewrite this as RT plus the max over pi t plus 1 to capital T of the expectation of epsilon t plus 1 to t of the reward function. Or in other words, this is equal to the max over mu t of the expectation of the current noise of my immediate reward. And if we look at the expression there, this is nothing but the value function again. And voila, we've derived one of the most important equations in RL. So that's the value function. And that basically essentially prescribes how we can do updates. So if you have a representation of a function, we haven't talked about representation yet. I'm just calling it a function, but you're going to have to code it somewhere in the machine. So if we have a function and we want to learn a function, this sort of prescribes an algorithm for doing that. Because essentially we start with a function, we compute this, and we get a new estimate of the function. So we could iterate this fixed point and hope that things will work out, that we will get a valid estimate. And indeed, you do, and there's many convergence results about you can show that this is a contraction operator, and you can show that this actually stabilizes, and you're able to estimate the value function. Now, there are also infinite versions or infinite horizon versions of this equation. And the infinite horizon is just exactly the same thing. But in the infinite horizon, what we have is the objective is a sum from t equals 0 to t, sorry, to infinite of RT. So we try to find the expected reward, even if those rewards went to infinity. And so what we then do is we introduce this thing here called the discount factor. And a discount factor, essentially, what it does is it's because we're exponentiating it to a power, it's going down to 0. And it just makes sure that immediate rewards, early rewards, are more important than future rewards. Now, choosing this, it turns out to be an extremely hard problem. And in practice, what you would want to do is marginalize this. And there are algorithms that try to integrate out this, put a prior on this, essentially like a geometric prior. And that gives rise to something called TD lambda and so on. I'm not going to go into it, but it's being able to decide, like to give you sort of an example why this is important. Imagine you're playing chess, and all of a sudden you win. And you have to figure out what all the actions that you took in the past were the decisive actions that make you win. So in a sense, there is a delayed, the rewards tend to often be very delayed. So the rewards are very uninformative, and all of a sudden, boom, your reward becomes very informative. And you're not quite sure which of all the actions were the ones that sort of mattered the most. So that's called the credit assignment problem. And it's one of the hardest problems to solve. Definitely worth a few PhDs if you can figure it out. Okay, so in the infinite horizon, we often try to maximize the sort of expected sum of future rewards, discounted rewards. And in that case, the value function of a state can be written as the expectation, just the same as what we have there over epsilon t. Oops, I forgot the max. And let's say that I just have a stationary policy, so it's the max over mu, or if it's stationary, I can just put an a. Because a is just equal to mu of x. So I'm just going to put straight a. And it's the same as that. So you have RT. And again, to emphasize that RT, in fact, I'm going to drop the t's. And I'm just, because there's a back, so there's time t at time t plus 1, I can just introduce some symbols. Right, sorry about that. I'm just going to rewrite this as SA moving to state S prime. And then there's going to be a discount factor, gamma V of S prime. That's a sort of formulation that you often find in books. So the only new thing here, I mean, I could have just called this epsilon and allowed for the function f, and then the notation would be exactly the same. But I'm trying to bridge it to the notation that you might see more often in the machine learning literature. The other new element here is this discount factor. But the same derivation that I just did, distributing the sum and the maxes, you could just put this gamma there, and you see that as an exercise, it's really trivial to get this other form of the equation. Okay, so often when you have a control problem, let me rewrite this again as a function, phi of s, just to illustrate the following. Let's assume that I want to solve this for a discrete problem. So my least favorite example, where you have a guy acting in the world, and I guess he has to move in this grid world and find a place where there is pounds, which I think is the currency that's doing well these days. And so he basically has to do this, so get a PhD and so on. Now you can map this, so this is a discrete state space, so you might want to basically find out what's the value of being in each cell, with this value of being here being higher than, say, the value of being here. And so in this case, this value function will look at all the discrete states, and there'll be one value for every possible discrete state. So this will be a vector, essentially. So you're going to have a vector that depends on b prime. This reward will be a vector as a function of pi. And we're going to have in this reward once you've taken the integral, once you've taken the expectation. And then we have a transition matrix, because associated with s prime, so the idea is I'm rewriting this now as p of s prime given a and s, as opposed to rewriting it as p of epsilon given a and s. So in the discrete state spaces, it's more convenient to just write it as a transition table. So for a particular, or in particular for a what this is a function that takes as input s and outputs s prime. So I can write it as a matrix from s to s prime times a v function. And so when you actually implement these algorithms, all you're doing is you're solving a linear system. And so the computation will, depending on how you solve it, will be n cubed or n cubed times n squared times the number of iterations. And all these different ways of solving this leads to different algorithms out there, like value iteration, false iteration. They're just ways of solving linear systems. Sometimes you take into account the structure, block diagonal structure of these problems, and you can even do standard machine learning techniques like belief propagation with EM algorithms, because this is sort of an expectation maximization problem, and you can actually solve for this. But I'm not terribly interested in that stuff, because discrete state spaces, they're interesting operation research. They will not give us anything remotely closely to what we aspire with AI. Okay, so I'm going to leave that equation there, and I'm going to switch to this board, and we're going to introduce the first algorithm for doing this, which is called TD0, and it's a stochastic approximation. In order to do stochastic approximation, I'm going to go back to this equation. I know this one or that one, it doesn't matter. Let's pick the infinite horizon one. And I have an expectation here. And so I'm actually first going to write, I'm going to remove the maximization step, and I'm going to make this a function of the policy. So this is going to be v pi expectation of s prime over s prime That is expectation over the probability of S prime given S R of A comma S S prime. And actually, I'm going to write here, pi of S plus the discount factor times the future value function. So I've just rewritten this. I've taken away the max operator, so now I'm just making it as a function of pi. And that particular expression, again, you can go back and you can quickly convince yourself that by distributing sums, you would get this. Now, this is a fixed point. I have v pi on the side and a v pi on the side, so it's like when you solve a linear system using Gauss-Seidel or the Jacobi iteration methods, if you've seen this before. But unfortunately, it has this expectation, which can be intractable for most problems, because in discrete state spaces, this will typically be an exponentially large expectation, soon getting you into trouble for all sorts of interesting problems, really, except the silly grid worlds. And even for continuous spaces, this might be a non-standard distribution, maybe products of t's and gammas and so on, which make it very hard to, or you might want to have a neural network here, which has some sort of interesting representation for the transition of the environment. So doing that expectation by hand is very hard. So it's, I think for all intents and purposes and practices, it will always be intractable. So what we can do is we can approximate it. Now, what I'm going to show you next is my recipe for my personal way of how I derive algorithms in this setting. So I basically, the way I go about this is I multiply both sides by alpha, and then I add b phi to both sides. Okay. Now I'm going to rewrite. I'm going to move this guy to the right, and I'm going to write b of s phi is going to be equal to v pi of s plus alpha times, I'm going to just write RT, plus gamma v pi of s prime. And then I have minus alpha, the alpha is a common factor. And I have minus v of s here. And I'm missing an expectation. I'm missing an expectation here, which should have been this expectation. Oops. Okay, so I have that expectation, and I've moved this here. So the next thing that I'm going to do is the following. I'm going to draw, I could draw more samples, but I'm just going to draw one single sample from the distribution of S prime. So I'm going to draw S tilde from P of S prime given S comma pi of S. And I'm going to approximate then this with V pi of S plus alpha times RT plus gamma V pi of S tilde minus V of S. All right, so I've drawn a single sample from the distribution to approximate this way. I could have drawn more samples, and then I would have done what I did when I did simulation, 1 over n, sum from 1 to n. But it turns out that to get convergence, you only need 1 sample. So it's the same as when you do stochastic maximum likelihood, or for those of you who've seen deep learning, when you do trying to train a Boltzmann machine or a log linear model, a CRF and so on. And that's it, that's the algorithm. So the only thing you need to do now is, so this is the old value function, this essentially is the new value function, so we can put an index over this. I don't know, over I plus 1. You have a discount factor here, and then this is I. So this is the old function, and I have some representation for this function. I haven't told you what it is. So if this is a neural network, it will be, this will be the parameters of the neural network in the previous iteration, and that will give me the new neural network of the new parameters. So to make this a bit more clear, it might be actually useful to look at this in terms of something we've seen before. Something that Zeke introduced us to. So in particular, if we have a loss function that we're trying to minimize, so you have some loss function of parameters and data with respect to some distribution that the environment that is producing data that we need to minimize. That's the classical scheme for minimizing a loss in machine learning. The data comes from here. So in particular, if you have data samples, we can, from the distribution of the data, then the problem takes the form minimize over theta 1 over n, sum from I equal 1 to n, the loss function of theta with values xi. Okay, so that's what we do in machine learning. We don't know the expected loss, so instead we minimize this empirical loss. Now, let's rewrite this as min over theta expectation of the loss of theta and x. What I'm going to do, I'm going to assume some regularity conditions, and I'm going to argue that the fixed point for this is grad loss of theta comma x p of x dx equal 0. And now I'm going to do exactly what I did in order to derive the TD0 algorithm. I multiply both sides by alpha. In this case, I'm in the parametric world, so instead of adding the function, I'm going to add parameters on both sides. And I'm going to draw samples from P of x. And I have my algorithm. Theta at iteration t plus 1 is going to be equal to theta at iteration t. I need chalk. Let's say that I move this to the other side, whichever is minimization, minus alpha. And then I'm going to draw, say, n samples. And let's say from n equal 1 to n, grad L of theta t, comma I drew the line too close to the edge. Let's write it this way. So that would be gradient descent, stochastic gradient descent. And it's stochastic because you haven't seen all the data. That's the only reason why we call it stochastic. Again, in stochastic gradient descent, we only need one sample. So we can just write it this way. Okay, and that's the version that we saw before. So the way to derive all these stochastic approximation algorithms is essentially the same. And that's our gradient, our friendly gradient descent algorithm to minimize losses. Now, why does this make sense? Let's do the following. Let's make this equal to theta t minus alpha grad L theta t from xt. And I'm going to add to this alpha times the expectation of the gradient of L minus alpha, the expectation of the gradient. So the expectation of the gradient being this expression here. So the true gradient. And so I can rewrite this as theta t minus alpha, the expectation of grad L, plus alpha times this difference. The true gradient, that is the gradient if I knew all the data of the universe, minus the gradient when I only know one single data point. Okay, and I'll close that bracket. So this is basically saying the stochastic gradient descent, this equation, is just gradient descent. Like if you ignore this term, that would give you the full gradient descent. But now we have this noise term, and this noise term is the discrepancy between the true gradient and the gradient at the current time step. Okay, so, and this is why this is stochastic, because it's not knowing the true gradient and only having the gradient times t. Now, this immediately, when you write it, I prefer it in this form than in this form. If you want to do theory, this is a nicer form, because when you look at this expression, you already see that what has to happen asymptotically is that this has to disappear. This term has to stop mattering, because you want to do descent in the true gradient eventually asymptotically. So in a sense, to make this vanish, it's nice to decrease. The first temptation might be, let's make alpha go down. And so folks often choose this to be 1 over t. Why does 1 over t make sense intuitively? Has anyone thought about it? What's the sum of 1 over t? Sum over t of 1 over t of the sequence 1 over t to infinity.
Log.
Pardon?
Log.
No, yeah, I heard the word divergence. So maybe forget t, imagine it's an n, sum of 1 over n, we did this in calculus, divergence. Now why is it a good thing that it diverges? Because you kind of need that because you need to go from the initial theta to any possible theta in the space. So if you're optimizing over the entire space, if this guy went to 0 too quickly, you might not visit the entire space. On the other hand, the sum over 1 over t squared, i.e. the variance of this, is bounded. And so essentially the reason why you choose 1 over t is when we do the analysis, we want to bound the variance of this noise. Bounding variances gives us bounds on probabilities, and we get convergence. However, if your space is compact, if you know the size of the box over which you're going to optimize, you don't need to visit the whole space. So in that case, there is actually an optimal eta alpha that is constant. Moreover, and there's some very good work by Nemirovsky and Shapiro colleagues showing that. Moreover, a good trick to do when you do this type of optimization, and it's true in RL, is to do something called Polyak averaging. So what you do there is you choose a fixed learning rate, sometimes a large learning rate. And so what happens then, let's do it with a picture here. If you go down the cost function, even if it's a convex function, it's a good, especially if it's a convex function, it's a good idea to do this, is to take big steps and oscillate. And then what you do at the end is you take the average, and boom, you get the optimum. As simple as that sounds, that is one of the most effective techniques for stochastic gradient descent or stochastic optimization algorithms. Polyak averaging. Take big steps and average. And essentially, you can show, and Francis Bach has a beautiful paper on this, that what you're doing is you're following a Markov chain when you have a fixed learning rate, and when you're averaging, what you're doing is you're computing an ergodic average. And he does some very nice analysis for this in the case of convex functions. So it's Francis Bach and Eric Modine. A beautiful, I think, 40-page math paper that is worth reading if you ever find the time and the love. Okay, so that's basically it. Now I want to just conclude with one last thing here that we're missing, which is Q functions. And I think for Q functions, I want to use this. And I will soon run out of time, so I'm going to just state the main results. And there's 3 lines to derive, but you can also define, just like I did for S, I could have defined a function over S and A, assuming that I start at state S and I start at actually A. And that likewise would have been the expectation over S prime over R plus gamma, and then I would have been able to distribute this action inside. So if I define the function instead of being in terms of ES, in terms of S comma A, then I can derive this particular recurrence following essentially the same type of work. This is called the Q function, or the Q factor, or the action value function. And if I apply the same trick that I did before, I multiply both sides by alpha, I add Q to both sides, I rearrange terms, I get an algorithm called Q learning. And Q learning is just the same thing as this method. So I wanted now to just give you an example of this. And how do I fancy? And then we can break for lunch. So in particular now I'd like to show you a little bit of what DeepMind did, which is actually an application of Q learning where the Q function is a deep net. That's basically it. And so we're going to update the parameters of that function. Pardon?
Doesn't like to turn off lights when it's
oh,
out
okay.
or cooling down.
And this guy
So coming.
Okay. So let's see an example of Q learning in practice. So now it got kind of dark, but it's okay. So what this company, DeepMind, did, what I really like, is they decided to create a reinforcement learning agent that basically just looks at the screen of the game, and then it learns to choose a set of actions to play the game. So just like a human faces a screen and plays with a joystick to win a game, this machine learns to play Atari games. So you have an environment, in this case the Atari simulator. You have a set of discrete actions. What's really interesting is the representation of state. You have images X, and then the state is a sequence of the images and the actions. So you're storing in your head a trajectory. And I really like that because of the following. Can you say the alphabet forward quickly?
A, B, C, D, E, F, G.
Now say it quickly backward.
No.
We store sequences, and we don't do random access. Say it for a number. You can say it very quickly forward. It's really hard to say it backward. It's a good test to see if you're drunk. And they also use discounted rewards. And sequences are really important. One of the founders of this company actually has a very nice paper where he shows, actually just very quickly, let me take you back here for a bit. So one thing so Quark will tell you all about these deep nets that learn local edge detectors in the visual cortex, and eventually as you go higher up, they learn Quark faces and cat faces and so on. So that's sort of compositionally making images out of small elements. But there is also neurons that are very interesting, called place cells or grid cells, that essentially fire, as shown here in this caricature. They fire indicating where a rat is. They're in the hippocampus. It's where we form short-term memories as well. And so in the same place where we're putting these sort of episodes of memory, these episodes of little video that we've seen, it's the same place where we're also composing plans. People that have damage to the hippocampus, they're not only bad at storing immediate memories, so they can't form new memories. Like there's another common patient, HM, I think, that had that issue and recently passed away. But also, you make plans, it seems, by pasting these memories. That's how you imagine and compose the visual world and you know, your dreams and so on. So sequences in the brain are really important. So I like this state representation for that, even though admittedly this is just an Atari game. So we're still in the 80s here, although these are pretty good. And then the Q function is, as I just defined, maximize over some policy the expectation of all future rewards. Now, that's the equation that I wrote now on the board with the Q function on top. But in this case, instead of having the true function, what we're going to do is approximate the true function with a neural network, like Paul will teach us this afternoon. And so that neural network, the Q function, will now have parameters theta. And I'm going to assume that the Bellman backup, for some data, A prime and S prime, that I will soon say where it comes from, is the observation. Why? And I'm going to try to fit the neural network to the Bellman backup. And that basically, if you take derivative, again, gradient descent from this, it takes this form. This is the very classic reinforcement learning with neural networks work, which is very old, but was never done well. So now where does the data come from? The idea is you're going to create a database where you're going to store states, which are sequences of actions and images, the rewards, and the sort of new state. So you're basically storing sequences on a database. Each sequence is they're denoted with the letter E, and you have a database D of those sequences. Now, in terms of the Q function, the parameterization is as follows. You take a video, you use some function, pre-processing function phi, that generates a set of images, and in particular, they use 4 frames. And you could use a different number depending on the game. And then you use a CompNet, which Cole will tell you about later today, which is sort of a cool neural network. And then there is a Q value at the output for each possible discrete action. So this is Q of A1, comma S, Q of A2, comma S, and so on. And that's the algorithm. So basically, it iterates as follows. For every sort of episode or trial of the algorithm, you start at some initial state. So you basically take the image, you pre-process it, and then something I haven't told you about yet. Q-learning is an off-policy method. So you are learning a Q function that allows you to choose the best action. But when you're learning that Q function, you don't need to use that Q function to take actions. You could use a different policy to take actions. These guys chose to use one of the simplest strategies in the world, which is epsilon greedy. I don't necessarily recommend it. I would rather recommend you to Bayesian optimization as an exploitation strategy. But the idea of epsilon greedy is to, with probability epsilon, you explore. You pick any action. And with probability 1 minus epsilon, you maximize the Q. You choose the action that maximizes your current estimate of the Q function. And then basically, once you have an action, you basically move the joystick, you move to the next stage of the game, you see what happens, there's a new state, and then you take this state and you store it in your database. And in order to do the backups, the gradient descent steps, what you do is you go back to your database, you retrieve these memories, and you update it based on these memories. And that's it. How to do this well is kind of what I think is really important. I'd love to understand better how to design very good databases where you could sort of plan and do counterfactuals and so on. And finally, another thing that's interesting that you can do here, an important thing that they did, they somewhat cheated because Atari is nice because there's a number on top that's, as you play, that's basically telling you this is how well you're doing. But in life, as we go about life, we don't have someone at every second telling us how well we're doing or how poorly we're doing, unless we're in a really messed up relationship. But there is another thing that really helps us going through life in a positive way, which is imitation learning. The other day I was in Edinburgh, I was walking down the corridor, I was staying at the hotel there, went to examine a thesis, took my daughter, she's like 1.5, she just learned to walk, and I was sort of walking down the corridor thinking, a very long corridor in this hotel, and then I looked back and she can hardly walk, and she also had her hands like this. So very cute, big belly. And so children imitate and learn by imitation, and like in this cute little picture here that I got from Google Images. And so you can do the same thing. You can actually let humans play the game and straight learn a policy. Now, once you have a policy, it's possible. I'm not going to go into that. That's another lecture. But once you have a policy, you can actually now try to learn a reward function. So this is called inverse RL. So given, you take an expert, you learn a policy that you fit the neural network straight to the data. Some of my students have done that. These are the kind of filters that they get, and so on. And then you try to learn a reward function, and then you play according to that reward function. So the idea is you first learn by imitating, you infer this reward function, and then you act upon the world. And as you go, occasionally you do get a new reward, and you have to update that reward function in a smart way. And I think being Bayesian about it is probably the right way to go. Finally, which one is human, which one is machine? Oh, but basically, this is a chicken and it's trying to cross the road. If you haven't seen this, I just realized there's a generation gap here. I just played this. And on the left there, you can see there's a score. So right now they're level 2-2. This is probably more interesting than the Brazil. Now, this is kind of like that. This is like Brazil, you know, slowly. And then occasionally bump. Yeah. No. Okay, so which one is human, which one is machine? How many people think this is the human? How many people think this is the human? All right, Liz. They're both machines. Just the machine learned from different experts. Thereby passing the Turing test. All right, thank you. Enjoy your lunch.
So you can check the perception. Yeah, I think I talk to this guy. Going to can you? Oh yeah. How far is
I like the combination. Like having
Yeah.
Well, I never seen before.
So you always use power?
These sports are all
We just But do you know any really rich people?
I do know a lot of rich people actually.
You ask me to donate to the Oxford?
Yes. Actually, Nando, did you want to head now or do you want to wait a bit? Take 5 minutes.
I'll take 5 minutes.
Got it. I stuffed it. Alright, so it's either
Layouts or something like that. Exactly, the cost is way more expensive. No. So the cost of the model and the training time increases a lot. So this is not.
That's a very interesting problem.
But it should be.
No, it's Jack plus that's probably a good name. So there are these guys.
Alex was too. What's the
I mean the other guy just because I mean this is basically people. So they tend to come up with especially they have a paper it's called multi-task based optimization, where they separate it into tasks, and tasks have different costs in terms of computation and so on. So they try to address this problem. The other thing is that there is a sort of multi-task approach.
So I've got,
But there's also some work that they do for neural networks, and that's what background data driven learning.
So, I wanted to get to
It's ranges of the last Writers of the lost current. So there they try to deal with the fact that you're comparing things, like you're doing basic optimization, but in a sense, you only need to optimize the learning rate for the layer once that layer exists. There's also a complication when you do think about it. And so they have a solution. I don't think it's that great. It's basically like this basic optimization that's okay, and then there's a little bit better. So the result is all impressive. It's a combination is very cool. Now we're getting but certainly the big move now is talking basic optimization model.
You know where Alex is?
The guys, I mean, these guys were doing okay. The problem is that they're all basically guys behind.
Yes, he came back.
So all the neural needs that's all.
Are you going to be after it as well?
So we can't get into development. There's the way the interesting is I can put in time for you who works at
talking to you guys.
So a couple of weeks, I should
bug
you.
I'm actually so there's a guy from money in Germany. He's very good.
Is it your code or did anyone else write the stuff in the other?
Frank Martin. He's very good.
I mean, I worked with my co-authors on that paper. But there isn't anything released.
Well, actually, this one here is like for early stopping with the ultimate here, how you should incorporate that.
Yeah, no, we can try to apply it to some of these.
But it's something similar.
Yeah, and I'm thinking with the object, so you pass on layers.
You use or like if
You're creating your
So basically,
You're setting up your end and then.
Yeah, I mean, this is one question people have been looking at. Oh, well, you know, is this cool? But, you know,
and also
something, and, you know, I really want to emphasize this actually is fairly general purpose level. So, yeah, the grid structure sometimes only naturally occurs.
I mean, I like
It's often like engineered.
So there's some nice frameworks now.
The
basics of challenge layered objects, parameters go somewhere, gradient,
He's proposing putting that.
And then it's a question of having someone who's very good at
neural data could be quite interesting as well. I mean, I have some neural data. That's really interesting because he collaborates a lot with John Cunningham.
Yeah.
I've never actually met him. I just started out last night randomly with he's here. Just one second.
And how do you make decisions using those features? Or
yeah, so a lot of the reinforcement learning in the past is you basically have very simple either linear models or discrete spaces.
okay.
And so now I think there are two things about it. One is nonlinear functions, but that has existed before. There was a lot of work with neural nets and reinforcement learning in the past. The neural nets now are back, so it's natural to revisit. Okay, maybe this didn't work before because we didn't have enough data, enough computing power. But I think there's sort of the episodic stuff, which is also all the idea of storing sequences. Actually, there's a guy here who invented it. He might just use it. So that's also coming back, and that's kind of interesting. Will this go much further? Who knows? I mean, Google's just got a company a lot of money to maybe take this further. We'll see what they can.
And do you want to
Oh, one quick question. Did the guys actually learn to read the score, or did they would they hard code it? I think I need to catch up with you.
I've also talked about
Oh, okay. Well, see,
if he ever gets out of here.
I would expect that because it's easy. Yeah. 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 But you don't have a time. You don't have Okay.
Looks like you have a next.
Oh, yeah, I did that. Alright,
Yeah, so I was asking like something that you alluded to yesterday, like in region optimization, they increase the variance of time. Why is that? Like because but the way I'm looking at it is if you increase the variance with time, then you probably would also compromise the quality. So
I mean,
yeah. Well, it has to be right.
watching, but it's not really participating. So it seems like all the knowledge here is honestly kind of like in this.
Right, and they think to
Yeah, or is it?
Oh,
right.
Right.
So the problem is that they designed to think about this long processing pipeline.
So and the way to meeting residents square.
They basically extend the data set sizes to whatever they can.
And the other thing, like, like high dimension also, the tree
parallel
something called SMART. So if you search SMART, sequential model. Yeah.
I like that. I just
So
personally
trees,
like that.
so there's SMART with trees.
Yeah,
And then the guy that has.
Yeah. Well, and serial.
And then the other one is just Google based on optimization, down dimension, high dimensions.
Yeah, right, it seems to be a little bit of a black art. I know that
That's
have a lot to do with making it's really
so do they also use
but I'm sure pretty much change in terms of
So then what we just what we exploit is the part
preconditionings on the
a
gradients.
lot of functions have
They
to
use a little bit of LVFTS type stuff, and they use rectified gradients instead of.
If this is one parameter, just around the symmetric
That was
as you move in this.
And it works, but perhaps we can get more powerful.
Change that much. Whereas this parameter.
And they do, so they use dropouts.
So-
They do about
So
4
this is the cost function,
Use dropout.
but it really only one unit. And so one way to deal with
Use
this
rectified linear units
cost
instead of
functions is to construct in a lower dimension projection of the line.
That's your,
all this stuff just seems like.
And I always search for the
oh, yeah.
because if you think about it, the location.
Well, yeah, I mean, this is interesting. I mean,
So I only need to search along the line.
completely agree with that. I mean, in principle, I guess.
And that's basically what it is. So basically, you stumble about some matrix. So in other words, you need to optimize f for x. Instead, we optimize f of a and y is the low dimension. So this way, it's sort of like this. So now y is low dimensional. So basically, I optimize y. Take it to the 2D,
And then you just put it in.
Yeah, exactly. That's a very simple trick. It works provided.
Yeah,
Right, some for the parameters, some of the
actual work.
If they're a little bit more.
And are they based on like, you know, like, what, relation of all the things, like, you dimensions?
So I had some
Yeah, the
conceptual
optimal dimension that you need to take,
too, because
No, we don't know that.
the best, like, the
Some
best
people have
algorithm.
tried to sell them and try
Right.
to come
This
up
is like,
with.
so the problem is,
the
the algorithm
algorithm
again,
should be
the algorithm will
Yeah,
actually use. Unless
The way I see it is super is forward on the
It's-
Yeah, so we are working on a similar situation where each of these function evaluations are quite expensive. But what we want to do is not just optimize the function, but like learn the high value regions of the function.
The one thing, the one
So you
thing.
can think of the function as say some log likelihood function. And what we want to do is say something like estimate the likelihood of the posterior.
That's
But like the parts of the log likelihood that's really going to affect you are the high value regions of the function.
Yeah.
So we want
that
to
is similar to what Andreas class. I don't know if you know.
Right, yeah, but
So Andreas class has a big recently where he was doing that. So basically, sort of just run projections and he's using Excel, and he's basically estimating the rate of the perfect shoot.
But I rather this complaint.
Cause it to perform well.
That's good.
Yeah. Yeah, that's how we work, right?
Yeah.
Yeah, I don't know. So I don't have a problem with capacity. These are the things that you don't know. So much access to capacity.
الو سلام خوبی؟ به این مشروع رو اومدم خیلی کمی یادم رفته شارژش کنم یه بود دیدی وسیط افزارم قطع شد. مرسی بعضیش خوبه بعضیش خوبه. آره 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 چی میگی کلاس دیگه چی میگی خوش میگی درس میگه از مطمئن کلاس هم من دارم کارا میکنم لپتاپ میارم میشینم کارا میکنم شقایق هستن دو تا دختر ایرانی دیگه هستن از کالیفرنیا یک گاروپ جایا آره هم ساعت نهار میکنم آره هم ساعت نهار یه جلسه روش میکنم آره آره شقایق چرا نهار داشت ولی نهارش دانشگاهشون شوهرش اونجا نهارش هم اونجا بود آره اسم رشته‌ام بود مشکل. نه دیگه مثلا مثلا مباحث مختلف و که تو درس‌های مختلف می‌خونی مثلا اینو به صورت خلاصه اینا اینجا تو 10 روز می‌کنی. پس چون خب مثلا آدم‌های معروفی میان درس می‌خونن. از فیسبوک به ایمیل داره بود که اسمش رو رو دیتابیسمون بگیم اینا بعد اینجا جا مثلا کرونا باشه شما بده بگم
Yeah, I actually can't find it better than that.
Oh,
Yeah. Yeah.
this is not the right.
Yeah.
Do you want it to be warmer or colder?
Feels really good in here, but I know. Just walked back from downtown, so. No? Why is that corner?
Yes, I mean, right across mass.
So what's it?
You're welcome.
It's like,
You want me to talk out and repeat this now?
might be because it's a registrar room, it doesn't have climate control. So I don't have- Really? Yeah. It's crazy.
Let me talk out.
Okay, that might be an intense conversation. I know, thank you for taking up. Holly and I were going to get up and still find a way to go. So we need to get ready.
If you look at the control room up there.
I don't know, I've never been there. You don't have access to it. Yeah.
Can you try to, I'll send you the RGB file. Can you try to access the, have you tried to do this?
No.
You need this password. You should have.
Oh, I mean, a Wi-Fi? Yeah. But it's kind of weird. I think it, I don't know.
Log in my Gmail account. I need to send a file. Just like it will direct you to
Yeah, it will.
I wonder if it would be possible.
I don't really know. I see there's some ports of laws. So for instance, they cannot access our build servers because they're on port 82. That is law. Did you notice the upholstery?
Oh, yeah.
Yeah, that's exactly. I took a picture.
I wouldn't figure it out.
No, just go to any page. No. No, I actually have a single. I guess my remark was really I assume that we cannot because the SQL is a block. I was able to use SSH besides that. 88, 81 are definitely something like that. Yeah. Yeah, it's on the internet. I don't know if the forest will. Can you do you mean the worst? Yeah. What do we need for our students? Which form do we use for all that? Okay. Then we're good. Right. So the basic only actually well. Then Marcus has this yeah. I really wanted to do the dry one. Talking about it. Because he comes in Sunday. I think it's about this coming. Anyway. Brian, you have to re-log in. I mean, let's do this minute.
Seems to share. It's grown. Was it? Was it already that way?
Hi, just missed the call. Yeah, oh. Yeah, just no,
I'm not sure if it's for me, I need to input my username. Any email. Works. Thank you so much. Okay.
Yeah. Someone took there. It's this one right here. Oh, this one. We've been actually wearing the other one too. So this one is. This is the speaker. The speaker system. So people are asking us all to use this. So you have to use those.
Both of them.
Both of them, yeah. You can put it up.
I'm very wide. Both of them.
Can you try speaking?
Fuck, you try to say something?
Does it work? No, it doesn't. I don't see the bottom.
Yeah. Fuck, can you say something more? Oh no, it's just this place. Okay, try it again.
Hello. Can
Yeah.
you talk a little bit?
Yes.
And I'll quickly restart the